only for the Bergeron process. Something like accretion of liquid droplets by ice and snow should also account for that kind of heterogeneity. And so they did a series of simulations of these Arctic mixed phase clouds, accounting for that phase heterogeneity only in the Bergeron process and then also in accretion. And so you're seeing profiles of cloud fraction on the left and cloud liquid water content on the right for observations in the dashed line, for the control simulation in black, when they account for phase heterogeneity only in the Bergeron process in blue, and then when they're accounting for it both in the Bergeron process and accretion in green. And at least in the case of cloud liquid water content on the right, accounting for that heterogeneity across multiple processes then kind of pushes the cloud liquid water content in the right direction. And so with that, I'll wrap up and kind of recall these three issues and point out some things that I think are helping us make progress on each one. So I point out this strong sensitivity of ice clouds to variables for which some of our observations have been limited or uncertain. And I think INCUS, in particular for the updraft question, is going to provide convective updraft measurements across the tropics. That's quite promising in understanding tropical ice clouds. The ARM archives are also beginning to build out these multi-site long duration records of INPs, and so that's helping us in better constrain our inputs of ice nucleating particle concentrations. Then I brought up these issues of structural formulation, how many and which degrees of freedom we need, and whether we need to necessarily represent all processes under all conditions. And here I think mathematical tools will be key to us. So I think things like machine learning, dimensionality reduction, sophisticated visualization of our model outputs are all sort of tools at our disposal to make progress on this question of formulation. And sort of toward this end, I want to highlight two studies that are pursuing that direction. Carl Lamb has used reduced order modeling of microphysical process rates recently. And there's a nice study from Ulrika Proska that uses an emulator to address requisite complexity within climate models for different microphysical processes. And finally, I highlighted this issue of inconsistency. And I think here, the primary tool at our disposal is just communication and talking sort of across schemes and specialties, sort of in line with what Johannes pointed out. And so there, I think meetings like the one we're having here are really our best tool to make sure that things are working well in tandem. So thanks very much for your attention, and I'm looking forward to discussion and happy to take questions.
But the issue two, I think it was how fancy does the representation need to be for what purpose is a really important issue. And I think for the ice cloud, well, so it seems like many of the ERF ACI and many cloud feedbacks depend a lot on warm clouds. Some of them depend on ice clouds. But how precipitation changes in the future, that is really going to depend on ice clouds, right?
Right.
So I'm wondering if people are doing, I mean, we do lots of studies where we look at cloud feedback and ERF ACI as we change the model. Are people looking at future precipitation as they change the model? Because I think that, I mean, it's also kind of a much more relevant question than future global mean surface temperature, right?
Yeah, at least at local scales, regional scales.
I mean, of course they're connected, but
yeah, I don't know of anything offhand. I guess perhaps because there are an array of different metrics that you could sort of look at associated with precipitation, whereas it's sort of more straightforward what the metric of interest is for radiation. Yeah, but I agree that we need more studies sort of focused on the effect of the ice phase processes on precipitation.
Thanks for the really nice talk. I really like this idea on focusing on simplicity and trying to reduce the processes to the ones necessary for the task at hand. But I worry then, and kind of this relates to Johannes's talk as well, how do we know which processes are important for feedbacks if we can't observe those changes in the present state?
Right. This is actually quite difficult to receive these sort of heavy questions.
Sorry about that.
I don't know what the answer is, but I think I agree that sort of observational constraints in present day that would indicate whether one process is more or less important are sort of a prerequisite for us to understand which processes would actually need to be included. So I think that that is a good point for discussion. We don't have a lot of these kind of process-based observational constraints for the ice phase. As far as I know, it's very difficult, right, to disentangle sort of signatures of different processes from observations. So,
no, I think that's a good answer. So they're necessary, but maybe not sufficient. They're an important first.
Yeah, thank you.
Yeah, thanks for the excellent talk, Sylvia. I'm curious. So one question that I kind of struggle with is which kind of bridges across your and your Hannes's talks is if we focus only on the warm cloud processes and try to sort of tune or constrain things through warm clouds, but we have this kind of big problem that we just really don't know how to do ice at all. There could be a risk that we end up sort of correcting for some problem that actually is in the ice phase by trying to tune the warm phase. Mm-hmm. And as you're pointing out, we don't really actually know the process rates for a lot of the ice processes. So I'm curious about your perspective on what the most critical observations are that we need, not just like, in particular, to what extent do we need laboratory experiments, like more laboratory experiments, either small scale ones or cloud chamber ones versus field? And to what extent should those focus on like getting information about like the known unknowns versus getting improved precision on stuff that we already kind of understand? Like we kind of understand warm rain better than ice. We all know that. But maybe like we could still improve our understanding of this. So this was a long kind of rambling question, but please, I
mean, on the question of lab versus field, I mean, I think the answer will always be, we want to do everything and make sure, like Johannes was saying, that those components speak to each other. I guess like Hugh has pointed out in his review article that I think lab work has been understudied or underdone. So I think there is probably more space for additional lab work. That's sort of what I would highlight personally. And then I guess, can you reiterate the second part of?
Well, I guess to be a little bit more pointed about it, how much marginal gain do we get from more lab work on warm cloud processes versus on ice processes?
Right. Yeah.
All right, this is good. So our next speaker will be Qingyuan Yang, and he'll be talking about detecting and identifying the impact of parameter interaction on climate model outputs based on 2 PPEs.
Okay, good morning, everyone. Thank you for coming to my presentation. I apologize for the change of the title of this presentation. Now it's called a new climate model PPE emulator that enables new insights on host model behaviors. So a little bit of background on the PPEs. So we generate the PPEs by first sampling from the parameter space, run the climate model, collecting the model output. The one key feature of the PPE is the sparsity. So normally you have several tens of parameters to perturb, but only you have a few hundreds of model runs. And the PPEs can be used to study the relationship between the parameters and the model output, used to train the emulators, and then used for the parameter tuning and uncertainty quantification. So when you develop an emulator, here's what we think about beforehand. The first is the parameter model relationship. So we are curious about how is it very linear or very nonlinear between the parameter and the model output? Are the parameters affect the model output independently, or they all interact with each other? And secondly, we're curious about, is there like potential ways like optimum ways to develop the emulator. So do we need one emulator for one variable, for each variable, or one emulator for all variables? We're curious, like if there is a potentially optimum number of data points we need. So maybe after certain points, we don't need that many, or it's just never enough. Should we focus on the climatologies or the model scores? And in our study, like we care a lot about the sensitivity, but this is very difficult to define, sometimes somewhat subjective. So with this in mind, we came up with our new method. It's simplified from additive Gaussian process, focused on the global, zonal, or local climatologies, works with one variable at a time. So this method is pretty simple. So it's basically a target variable is decomposed into the sum of the means of Gaussian processes, and each of the mean corresponds to a single parameter or 2 or 3 parameters. So the big simplification we did here is we fix the Gaussian process hyperparameters. So we don't estimate it, but it will be tested later if it has a big impact. So this slide is a little bit overcomplicated, but basically what the method do is, so we have the format of the additive terms. We just need to define what are these parameters are. So it does it through the iteration. So first, we focus on the target variable, fit it to all the parameters, just individually, and find the parameter that fits to this variable the best. And we use it as the first additive term, and there are some residuals. So we we put the residuals to the next iteration, and doing the same thing, find the second terms. So this is the iteration, and for single parameters, but for parameter groups, we came up with this measure. So we select the parameter groups not using the root mean square error. So we just use a measure that highlights the additional benefit of emulating the 2 or 3 parameters jointly compared to emulating them independently, hoping to highlight or like better capture the parameter interaction. So because the method is additive, so you would imagine as we have more terms added, the root mean square error gradually decreases, which is shown in here. So the x-axis are the parameters or parameter groups. And you can see the red bar, the difference between the points are the kind of the explained variability for a certain parameter or parameter group. Moving on to the test case, it is tested to 2 sets of climate model PPEs. They're different in the number of ensemble members, the model themselves, and the range of the parameters. So we compare its performance with neural network, which emulates all variables all at once. And the target variables are a combination of global averages or model scores. And so using R squared. So the x-axis here are from a neural network, y-axis are method. Each point is a target variable. The bars denote the variability from just repeat random sampling tests. So you can see for the CAM6, it's kind of evenly distributed along the one-to-one line. So the performance are comparable, but the variability bar is very big. And that is because we're modeling lots of model scores, which compress lots of useful information. So a -1 and 1 with observation of 0 compress these two into 1. So if we focus just on the global climatologies, which is shown on the right, both methods performance improve and the performance is comparable. So moving on to the model E3 PPE, you can see overall the performance of the 2 methods are better than CAM6 PPE. And I would say neural network slightly outperforms our method. So there's more points in the lower triangle. But interestingly, there's this one variable that our method, total ice water pass, that our method always outperform in emulating. So I'll try to explain why. As mentioned before, we fixed the hyperparameters, which is a little odd. So we tried very different Gaussian process hyperparameters. So we fix them and test their variability. So this variability is shown in the x-axis. Just a reminder, in this case, both x and y-axis are using our method R squared. So here, the y-axis are the variability, the bars are the variability you've seen here. So the horizontal bars are very small, showing that the impact of hyperparameters is relatively small. So we've compared it with neural networks. So now let's compare with linear regression using the CAM6 as an example. Just focusing on this one, convective precipitation. Blue are the kind of the explained variability from linear regression. And the yellow and red are the ones with our method excluding and including parameter interaction. So the higher the better. So with this, I think we can say that at least the relationship between the parameters and targets is a bit more complicated than a linear relationship, at least for some variables. That's what we need to stress. So this figure is just showing kind of the traditional heat map, but the color here are not the linear correlation or coefficient. It's more like the variability explained by our method. So the y-axis are the variables, x-axis are the parameters. The green shaded area are the parameter group explained variability from parameter groups. So these are the relationship that would be likely ignored, or if you examine the linear relationship. And we're showing a good result. So for the model E3, there's a lot of interesting parameter interactions or their impact. So that's what we're going to focus on in the following presentation. So just a quick example of some important parameters and parameter groups. So this is DCS, which is the threshold for auto conversion, and then DCS and VF multi, which is I think coefficient for falling speed. And here we're moving back to total ice water path. So I want to explain to you why our method works better in this particular case. So looking at this white band horizontally, you can see there's only a few points that are very colorful, which means there's not that many parameters that greatly help explain this variable. So that got us confused because so if there's not lots of parameters helping explain this variable, why a neural network doesn't work well. And it seems like the answer is lying in the vertical white band here. So it's a VF multi S, which is I think ice falling coefficient, speed coefficient. So this parameter is very kind of lonely. You can see only there's one orange point that they intersect. So this is a very easy but standalone relationship between the total ice water path and this VF multi S. So when the neural network emulates it, during the training, you could imagine it focuses on all the variables. So it wants everything to look good. And the many other variables are somewhat correlated. So this standalone relationship is very likely omitted by neural network. And that's because our method works with one variable at a time, and that's why it succeeds in this particular case. So the question of should we emulate all variables all at once? So probably not. This is the further summary of the figure before here. So the y-axis again are the variables, and I'll just summarize it for you in case it's too complicated. First, we find that the cumulative impact of individually insensitive parameters could be important. So that you can see the light blue and gray bars, they are the summed explained variability of parameters that only contribute to less than 5% of the total variability. So their total length is big, which means their total effect is kind of important. And the intuition is very simple. Imagine a linear relationship here. So from x1 to x45, they all have very, very small slopes. But when you add them together, there could be a large ratio. And also the yellow and orange are from parameter pair interaction. So they are small, but not negligible. Occasionally there's some very red bar, which are from parameter interaction of 3. So this shows there is some parameter interaction, and it's mostly parameter pairs and parameter groups of 3, at least for the model E3 PPE. And as I said before, our method focuses on just each variable independently. So of course, the target variables could be correlated, and you should include that information in. So we just pick some green points here. So this is the one you've seen before. So neural network outperforms in emulating these green points. So we focus on them again, but this time we manually select some target variables that it's easy to emulate by our method. And we use these variables as like input to train our method again, and the results are shown as the blue point here. So I'm sorry about the poor color contrast, but all but one variable leads to a degradation in the performance, but they all become closer to the one-to-one line, showing that we should take into consideration the correlation between the target variables. So we shouldn't emulate them all at once or one at a time. So maybe we should group target variables and emulate them separately. And another thing is always about the number of data points we have. So we just focus on the green band, again, using two variables from the model E3 as an example. So the x-axis are the number of data we use to train the emulator, and the y-axis are the explained variability. You can see for some variables, it increases and then plateaued, which means that so we have, if we want to be really economically savvy, we should always run some batches, analyze how the emulator performance changes with that, and when it plateaued or meets what we want, a certain level of accuracy and etc., we should stop to be more productive. And then this is just a quick summary. So as you can see, the performance of the two emulators on the two PPEs are very different. Obviously, there's a difference in the models, and also the PPE range, parameter ranges are very different. Not very, but slightly different. So the takeaway is, when we make interpretation on the emulator performance and interpreting the PPE, we have to keep in mind that all these are conditioned on the specific PPE, because they're all different. So for our ongoing work, we focus on the uncertainty, of course, and the focus of the focus is the outliers. So, you know, we always saw some outliers, but they're not errors, because they're still like output results from the climate model. So it's better to kind of find out why and how they occur, what parameters are responsible for that. And we're focusing on the regional climatologies to explore new relationships. So this is just a summary of what I've said. There's a new method, but more importantly is that from this comparison, we feel like these insights could benefit future studies on the PPE and emulator design. And feel free to try our method and give a lot of positive or negative comments are all welcome about our method. Thank you for your attention.
All right, so our next speakers will be Nicole Riemer, and she'll be talking about structural uncertainty in aerosol model representation.
All right, thanks for the introduction and the opportunity to speak here. Before I launch into my talk, I would like to acknowledge my collaborators, Jeff Curtis, my grad student, Sam Frederick, and my longtime collaborator, Matt West, and the funding agencies, NSF and DOE ASR. Okay, so I'll bring the group here into the world of aerosols, and I would like to confront you with this picture of real aerosols. This could be the aerosol state as we measure it at any location, at any point in time in the ambient atmosphere. And you immediately recognize, of course, aerosols are these complicated things. They come in many different sizes. Even within a certain size range, there are many different compositions, shapes, and morphologies. And so as an aerosol modeler, this is what we are up against, right? So somehow, as we develop our aerosol models, we need to simplify to make this problem tractable. And so there are many different ways to simplify, and no one right way probably to simplify. And this is the cause for structural uncertainties. And so if you look at our famous IPCC chart that tells us that aerosol cloud interactions and aerosol radiation interactions introduce a lot of range in the predictions. One of the reasons is that different aerosol models are structured differently. And so it's no surprise that we get different answers if we try to calculate the impacts of aerosols on climate. Okay, so what are our popular choices when we design aerosol models? Going here from the left to the right, we go from very simple. In case of bulk models, we just track the mass concentration of different aerosol components. So the different colors stand for different chemical species. A bit more complicated or a bit more complex are the modal models, where we represent the aerosol population with several overlapping log normal modes, and each mode can have its own composition. Only certain species are allowed in certain modes, and so there's a lot of judgment, how do we construct these modes, and how many modes do we have, and what are the rules, how these modes are interacting. But we do treat size and differences in chemical composition within certain size ranges, but within one mode, all the particles are assumed to look the same. Sectional models are quite similar. We track the size resolved composition, again, within one size range. We only know the average composition, and we cannot resolve diversity in composition or shape within that size. And then most computationally expensive, but most detailed are particle resolved models, where we throw away modes and sections and let the particles be particles and let them evolve according to the processes that the particles experience in the atmosphere. Now we are not constrained to assuming all particles within one size range have the same composition, but of course this is computationally much more expensive. And I want to shout out to Laura Fierce's talk on Wednesday morning, where she talks about confronting structural uncertainty in aerosol cloud interactions through process level benchmarking. I think our community can do a lot in that regard, just comparing our box model simulations from different aerosol models and what the differences are, and quantifying this in a rigorous way. Okay, so I explained how aerosol complexity can lead to structural uncertainty, but there is another dimension to it, and so that is the spatial resolution, how well we resolve space with our models. And if we think about aerosols, there's a lot about how well do we resolve emissions. The chemistry is really nonlinear, right? And so if you have a finer resolution, you're resolving the emission patterns much better. And so if you go to coarser resolutions, you are smearing out everything, and chemicals that are interacting in the real world are actually interacting just because the grid resolution is so coarse. Just two examples of different models where they sit in this space. Models here on there we go, on the large scale, and they use these more approximate models, and then the chemical transport models here in the middle used quality forecast. And on the right hand side, the types of models that we have the past few years, the particle resolved models, the regional scale, most recently all the S scales. And so this is what I do focus for the remainder of my talk. Starting out with WRF part MC, particle resolved model on the regional scale, where we look into these issues about what does simple CCN predictions. What is part MC? It's a particle resolved model, and I should say particle resolved models are very similar to what the super particle in the cloud physics community. Particle resolved model MC to WRF. So WRF supplies our fields and moisture fields and temperature, and in box is little part MC simulation happen. We track many individual particles, and so is in case recognizing this is California, this is the Bay Area here, so we have simulations for the years back, and so we often display our output here size on the x-axis, and then on the y-axis another quantity. Here in this case it's the organic carbon mass fraction, and so then the color is the number concentration of this 2D histogram space. Immediately at one size, let's say 100 nanometer, there are many different organic carbon mass fractions possible. In a sectional model, this y-axis here would collapse, right? You would have lines. And so we can in further pick a certain particle. We know what it's made of, what the components are, and we also track the sources where these particles come from. So there's a lot of information in Ritzel about the aerosol state. Now, what we can do, this type of model output, the left-hand side, our model real aerosol state, meaning our best effort, how to simulate our aerosol population, where each particle can have its unique composition. We can play things like this, where we say, okay, let's assume we don't know all this completely, but we assume an internal mixture, meaning all particles have the same average composition, the same as the bulk, and we assign that composition to each particle, leaving the size untouched, right? And so this would be what we call composition averaging. And then we can go the other direction, which is another popular assumption that more simplified models take, the external mixture, where we make each, again, the bulk composition is the same, but each particle consists of just one species. And so the question is, what does this mixing state simplification have for an impact if we want to know things like CCN concentrations? And so this is a little bit of a busy plot, but I'll walk you through here. The top is the reference, our best estimate coming from our particle resolved model at one particular grid point, somewhere in the model area, model domain, just to illustrate how this works. So we can look at black carbon mass fraction. Again, on the x-axis is particle size. On the y-axis is the amount of black carbon in our particles. And you see there's a continuum of particles. Some contain a lot of black carbon, others contain very little. We can look at other chemical species. A sulfate, for example, looks like this. A lot of sulfate-rich particles, sulfate-poor particles, and lots of things in between. And I haven't shown all the other chemical species, which we also know, but they're not shown here. This translates in a particle hygroscopicity, again, as this 2D histogram. Many different hygroscopicity. These are the sea salt particles, and down here are the carbonaceous, freshly emitted particles. And then we can ask each particle, what is your critical supersaturation? And it looks like this, right? Some need a lot of supersaturation to activate, others don't. And eventually we can construct a CCN spectrum. So now there's supersaturation on the x-axis and the activation fraction, and the green line would be our best estimate from our particle resolved model simulation. And now if we project this true, or our best estimate, into internal mixtures and external mixtures, everything looks much more simple, right? You have these averaged lines now, and this is done, by the way, in certain size regimes. It's not averaged over the whole populations, but in certain size bins. And then for the CCN spectrum, you get the red line for the internal mixture and the blue line for the external mixture. So the error in CCN is the difference between the green and the red and blue. And you can see it depends on the supersaturation level. For the low supersaturation, in this particular case, we would get an overestimation for the high supersaturation for the internal mixture, still an overestimation for the external mixture, and an underestimation. And as a map, it looks like this. This is a particular snapshot in time, 5 p.m. afternoon time on the second day of the simulation near the ground. Shown is the error in CCN concentration. Red is the overestimation. Blue is the underestimation. For the internal mixture assumption, you get overestimation everywhere. And so the reason is you are smearing your hygroscopic material over the entire population, even though some of these particles actually don't have a lot of hygroscopic material. And for the external mixer, it's actually more complicated. And we can talk about this later. We know why this happens, but there can be overestimations or underestimations depending on the supersaturation threshold and the underlying actual mixing state. Okay, so this was the PART-MC example. And for the last few minutes, I'm going to talk about an application where we use the WRF PART-MC in LAS mode to look at spatial heterogeneity. And so our thinking here is, okay, so the emissions are changing very quickly if you look how it changes with space, right? And so what is the impact of these spatial heterogeneities on aerosol subgrid processes such as coagulation and the chemical reactions and gas particle partitioning, which are all nonlinear processes, and how does it eventually impact cloud properties? And so Here, just a quick overview what our model domain looks like. These simulations are way more idealized at this point. So we're looking at 100-meter resolution here, a model domain of 10 by 10 kilometers. And in each grid cell is a little PodMC simulation sitting. And now we are comparing cases where we compare to an averaged, spatially averaged emission pattern that is a proxy for a coarse resolved model. And we compare this, we modify the emission pattern by putting the emissions into different spaces in our model domain. So this, for example, would be like an urban-rural interface where all the emissions are on one side and no emission on the other side. This would correspond to a road. And if you look really closely, there's actually one grid cell that has all the emissions now resembling a point source right here in the middle. Okay, and so then just jumping to the results here, if you look at profiles of CCN concentration, so now we have height on the y-axis and the concentration of CCN on the x-axis, comparing our 4 different simulations with a different emission pattern. The dark line is always the uniform base case, and then here in this case we are looking at a supersaturation evaluated at 0.1%, or CCN evaluated at supersaturation of 0.1%. And so what happens is actually the increased spatial heterogeneity has competing effects. For one thing, we get more coagulation if we have a highly heterogeneous pattern. And this means less CCN because you are coagulating the CCN away. But we also create more, in this case, more nitrate in the upper boundary layer. And so this means we make the particles bigger and more hygroscopic, which means more CCN. And whatever wins out depends on the environmental supersaturation. In this case here, we get more CCN up in the boundary layer and less CCN near the ground. And the high supersaturation case is a bit more complicated here with first an increase and then a decrease. And I think my time is up. And I come to the summary. So what's wrong with the microphysics and climate models? I really like Johannes' analogy or picture with the puzzle pieces. So this presentation was about the aerosol state puzzle piece, coupled to the spatial resolution puzzle piece is, I think, a key problem in our models. And I showed you a framework of how to use high resolution aerosol transport models to develop benchmark cases that we can evaluate more approximate models. So thank you for the attention, and I close here.
So our last speaker for this morning's sessions is Hassan Beydoun, and he will be talking about the relationship between condensate lifetime and precipitation efficiency and the responses to sea surface warming.
So thanks everyone for attending, and thank the organizers for giving me an opportunity to talk about what we've been doing at LNL in terms of trying to understand how these 2 interesting metrics, precipitating efficiency and condensate lifetime, both of which are kind of encapsulate the kind of micro to macro theme, how they relate to each other and how they respond to temperature, sea surface temperature, specifically in idealized simulations. So first, just to start with some definitions, what is the precipitating efficiency? It's a ratio of your precipitation divided by your total condensed water. So if your precipitating efficiency is 10%, it means you actually condense 10 times more water than you precipitate. And I have a few papers here that are sort of my favorites about precipitating efficiency that show us how important precipitating efficiency is in communicating microphysics to its large-scale environment. So there's a nice theoretical/idealized model paper by Roms, which shows that the precipitating efficiency is a key metric in determining the relative humidity of the tropics, which would go a long way in determining things like climate feedback. There's a really nice paper by, well, it was a kind of a theoretical foundation by Carrie Emanuel, and then some actual idealized models to validate that theoretical context by Nader and his colleague, which shows that for a fixed radiative cooling, your precipitating efficiency sets your convective mass flux, which kind of is consistent with intuition. And then finally, probably my favorite paper and the one that kind of captures the power of precipitation efficiency is this Zhao et al. Paper, which shows that you can reproduce the entire CMIP spread in climate sensitivity by just tuning this parameter, which in GCM's precipitating efficiency is actually a set. It's a tuning parameter, not like cloud resolving models where it's something that you resolve. So in summary, this epsilon term encapsulates this micro to macro interactions, especially in the deep tropics. So I think it's very relevant for this workshop. So there's also this other interesting term, which is this condensate lifetime. So fortunately, Sylvia already introduced this for me. She did me a favor. And this one's actually the precipitation divided by the total condensed water path. So it actually has units. It has been suggested that it can be a proxy for the precipitating efficiency, but it's really a lifetime. So it kind of begs the question, what does it mean for it to be a proxy? And how does it really analytically relate to the precipitating efficiency? The really exciting thing about this term is that in RCEMIP, which is this intercomparison model, intercomparison project of idealized models run in RCE, the inverse lifetime, tau inverse, shows an increase with SST for 32 out of the 36 models. And if anybody has any experience with these models, they don't tend to agree on much. So it is interesting that they agree, or at least qualitatively, on the sign of how tau inverse responds to warming. And you may think, okay, well, the fractional change is massive, but kind of in the SST RCE world, we tend to look, we're still at that stage where we're looking for like robust changes in the climate signal. So then we got two questions here. How does this tau inverse does a tau inverse increase indicate a precipitating efficiency increase? And then what processes are responsible for the tau inverse increase? Because there seems to be a robustness across models. So it begs the question of there are microphysical processes that models agree on. We should know what they are. So to that end, we do some math and we develop 4 equations that kind of encapsulate what I want to talk about. The first is the relationship between epsilon and inverse lifetime. It's really easy to obtain this relationship. All you have to do is divide by the total condensed water path in the numerator and the denominator, and you get a nice expression up there, which shows you that epsilon, yes, is related to the inverse lifetime, but it's in the numerator, it's in the denominator, and there's this other elusive term, which I call the evaporation inverse lifetime, which is much harder to measure. So you have a term that's hard to measure, a term that's easy to measure. What I mean by measure is in observation, you can actually measure it, and then something that's also difficult to measure. So kind of this is a little bit of a, just shows you that it's a little difficult to, you kind of have to account for this term before you understand the relationship between the two. Furthermore, we still want to understand what's going on, what microphysical processes encapsulate this inverse lifetime. So we do some math. The math is not that complicated, it just looks complicated. You do a budget on the precipitation, and you do a budget on the evaporation, and you achieve a bunch of equations. The first is the inverse lifetime, which shows the inverse lifetime relating to microphysical lifetimes. The A here, tau inverse A, is the lifetime of conversion from cloud to rain. The sedimentation is the lifetime or the time scale for bringing the precipitation down to the surface. And then finally, this precipitation evaporation, which is the lifetime or the inverse lifetime for evaporation of precipitation. And then there's this inverse lifetime evaporation, which is related to both the cloud evaporation lifetime and the precipitation evaporation lifetime, with this fractionation, FP modulating the balance between the two. And finally, what is this FP? Well, it's also related to the lifetimes. Specifically, it's the ratio of tau A inverse divided by the sum of all the other inverse lifetimes. So now we have 4 equations, so we can just go ahead and apply the chain rule on all of them with respect to sea surface temperature, and we can see how all of these different things are changing. So for that, we use RCE simulations. So we have a nice ensemble, kind of a mixture of different models. So all of them are the unaggregated RCE simulations, which are 100 kilometer by 100 kilometer domain. Here's a nice visualization from Muller and Held in 2014. These are constant sea surface temperature, pretty homogeneous conditions. We did our own in-house SCREAM simulation. So SCREAM is the simple cloud resolving E3SM model. It's the E3SM model run in at 3 kilometer resolutions, cloud resolving scales. So we did those, and then we also snagged the SAM results that were produced by Lutsko and Cronin for their precipitating efficiency study in 2018. And we also take advantage of Giovanni and Jiu's minimal recipe simulations, which I really like. So these are really minimal recipe in that the only microphysical process rate is the conversion from cloud to rain. And then you produce these constant sedimentation velocity raindrops that don't evaporate. So it's really nice. And there's 2 ensembles for those, one with accretion and one without accretion. And once we add accretion, we can kind of understand how that additional nonlinear microphysical process rates impacts the inverse lifetimes that we're interested in. And so finally, for all simulations, we use domain mean averages and apply the chain rule on the 4 equations that I show. So the structure of the results, I just have the equation that I'm interested in here at the top. It's the 3 different models and with the ensembles that they're run with. So the SAM one has 3, screen 1, and then the minimal recipe has 2 for one without accretion and with accretion. And so we start with this one, which is the relationship between epsilon and tau inverse. And we see for both SAM and screen, there is an increase in epsilon with warming. So for SAM, it's for all 3 ensembles. For screen, it's for the one we have. But we see a much stronger increase in the tau inverse. And that's because there's a simultaneous increase of the evaporation inverse lifetime. And this is kind of physically consistent with our intuition in that as you warm, your atmosphere produces larger saturation deficits, and it becomes easier to evaporate condensate. So it becomes easier to evaporate condensate. It also becomes easier to rain out. So these are 2 competing effects that may or may not result in an increase in precipitating efficiency. For these 2 models, it does seem that the tau inverse term wins out, and we see it increase. But mind the scaling. You can see much larger increases in tau inverse compared to epsilon. For the minimal recipe simulation, so different scale here, none of these are really systematic changes. We just see a decrease in the tau inverse in the first ensemble, which is the super minimal recipe one, the one without accretion, and we're going to get into why that's happening. But in conclusion, the minimal recipe, which kind of sheds itself of microphysical complexity, does not produce neither the increase in tau inverse nor the increase in precipitating efficiency that we see for the full complexity simulation. So that's interesting. Now we want to kind of understand what's behind this tau inverse and relate it to the fundamental microphysical processes. So we do the same thing, and we see increases kind of across the board. So as for both SAM and screen, as the sea surface temperature increases, you see increases in everything, in the conversion from cloud to rain, and how quickly you can sediment out your precipitating particles, and how quickly you evaporate your precipitation. And so everything's increasing. Obviously, the tau precipitation inverse works against the other 2, but the other 2 went out, and you see the systematic increase in tau inverse. All ensemble members again, and screen. And we see that what's responsible for that on the whole are both the increases in your cloud to rain conversion lifetime, as well as an enhancement in your sedimentation lifetime. So as the atmosphere gets warmer, it's easier to convert clouds to rain, and it's also easier to get the precipitation down to the surface. What's going on with the minimal recipe is a little bit more interesting. For the one where you don't have accretion, where you only have autoconversion, you see a decrease in the tau inverse, and that's because, well, in this case, tau A inverse, because the accretion is a simple, a simple form that has a prescribed tau that's fixed, that's going to be constant. So that doesn't change with warming. There's no precipitation evaporation, but there is sedimentation. Actually, what happens there is because your sedimentation velocity is constant, you just get the effect of the rising clouds. So the clouds rise. Now you have to traverse a longer trajectory if you are a single rain droplet. And so your tau inverse actually decreases with warming. Once you turn on accretion, you get the impact of the enhanced conversion from cloud to rain. And then those 2 kind of compete with each other and give you sort of a more or less constant town inverse warming. So we can now use this framework to understand why the minimal recipe simulations don't exhibit the same behavior that the full complexity ones do. So what about the inverse evaporation lifetime? So that one is a function of three things: the cloud evaporation, the precipitation evaporation, and the fractionation term. For both SAM and SCREAM, we see just increases in the tau cloud evaporation as well as the tau inverse precipitation evaporation. So again, both, it's easier to evaporate clouds, it's easier to evaporate precipitation. So we see increases in tau inverse. Minimal recipe simulation, very interesting again. You actually have this impact of the fractionation. So as you warm, more of your condensate is sitting in precipitation form. And because your precipitation doesn't evaporate in the minimal recipe simulations, so you actually are shifting your hydrometeors from this phase where you can easily evaporate to this phase where you don't evaporate at all. And that results in a decrease in the tau evaporation. So then the fractionation, because for that last set of simulations, we did see this interesting behavior in the fractionation. And we also see kind of increases across the board. And specifically for the minimal recipe, because I'm going to emphasize that one, that's the one where the fractionation ended up setting the response of the tau evaporation term. We see an increase in fractionation because of both the decrease in the sedimentation lifetime as well as the inverse lifetime, as well as the conversion lifetime for when you turn on accretion. So you can understand things with this diagnostic framework. Nice. In conclusion, how much time do I have? Oh, I have 0 minutes. Okay, so I'll just say that tau inverse and epsilon are not the same thing. They're both interesting. And we've developed a diagnostic framework to understand the link between this macro scale physical process rates. Thank you.
All right, thank you. And thank you to all of our speakers. So at this point, we have about 40 minutes for open discussion. So in order to minimize running around with the microphone, if the speakers, if you're not already sitting near a microphone at the front, if maybe you could sit at the front so I can run around with my microphone. Okay, so if you have a question that we didn't get to yet, or a question that you want to come back to, if you could come to one of the microphones. We'll start over here with Ken.
Okay, thank you. Yeah, Ken Carslaw from University of Leeds. I wanted to pick up on something that Johanna said, which I think is a really good point, that what's wrong with us? I think and you made that really clear, and I think the need for integration. And one thing I've noticed working on trying to get a synoptic view of uncertainty and how to reduce it is how many proposals I've reviewed that say we're working on this really detailed process because it's really important to reduce uncertainty in climate. And they're not going to do anything of the sort. They're never going to reduce uncertainty with that approach. And it's not their fault because they're constrained by the size of their proposal. It's never going to be able to integrate as you want. And I find that very frustrating because I think many of us have in our mind a very clear procedure for taking a lot of process-based research and using it to genuinely reduce uncertainty. And we're not doing it because, and I think the problem is not us, I think it's our funding agencies. They're not providing the long-term vision and mechanisms for doing the science that we want to do. I think we really need to change that. So there was a study a few years ago by Hope that said that, quite an apt name, that climate uncertainty costs trillions of dollars. We continue to do our science, I would say, rather badly. We should get better at doing our science that we know we can do. So I just wanted to throw that out there. And it's for the funding agencies. I think we need to internationally do it in a much more optimum way.
Yeah, thank you for saying that, Ken. It's really true, and it's such an important problem. And either we can solve it or we can't, and we should find out. But we're not doing that right now, and it is extremely frustrating. Yeah.
Yeah, I think in 10 years' time, no one will care. Actually, I think climate will have changed, and they'll have moved on. We have a short time window to do something about this, and I think we should really get better. And I'm really optimistic because we have so many ways of working now that we know we could do it. So let's try and do better.
All right, we'll get to Hugh next since he got sent back to his seat earlier.
My question is a lot more specific than the last one. This is about Sylvia's talk. I was interested in this issue of the structural uncertainty, and in my mind, one of the main issues is ice categories, which you sort of alluded to when you talked about cloud ice versus snow optical properties. Is this something, well, I guess my argument would be maybe we can just move away from having separate categories. Been kind of harping on that for probably 10 years now. This is maybe something we can just talk about in the cold cloud discussion too, since this is a bit specific, but something to consider when I think just thinking in general about structural uncertainty of these schemes, about these set of prognostic variables that are involved with them, to me is a key thing, in addition to the process level kind of structural uncertainty that you had mentioned in your talk.
Yeah, I think that's a great point. Yeah, I focus more on inputs, right? And like sort of the inputs that are going into the structure and the structure itself, but then also like what the outputs of that structure are also an important component. So yeah, agreed. Artificial partitioning of outputs doesn't help us.
Yeah, go ahead.
So what is your alternative? Is this similar to, when I think about the aerosol world, the classes would be, you have your sea salt, your dust, your carbonaceous, and nothing in between. And so how do we create a model that actually can resolve the in-between states? Or
yeah, I think it's basically centered around prediction of particle properties. And there are a handful of schemes now that are moving towards that. This is also more similar to how detailed models work, especially Lagrangian models now. There are, you obviously mentioned that in your talk, but there are a few Lagrangian particle-based schemes that include both ice and liquid phases now, and they are based around this particle property approach. So I think in terms of bulk modeling, it just is moving in that direction of more process-based kind of detailed modeling where it is.
Yeah, so I want to come back to my question from earlier since we didn't get to discuss it and maybe elaborate on it just a little bit more. So the question that really I have is, in the ice processes community, there's now a very, very clear understanding, and I think a pretty broad consensus, that there are a lot of sort of fundamental processes that we just do not understand enough and that are absolutely going to require laboratory experiments to really get the process rates. Something that's less clear to me is to what extent that's also true for warm cloud processes. And what I heard from the talks this morning is that the uncertainties that we are really struggling with in warm cloud processes have more to do with interactions at the mesoscale and things like turbulence, things like what to do about subgrid heterogeneity. So I'm curious about perspectives on this, and this is mostly a question probably to Johannes and Sylvia, but others may also have comments.
Well, so I guess I did my warm rain studies like 5-ish years ago, and I think knowing what we know now, so Caitlin has a talk on this tomorrow. It's maybe what I was doing was asking the wrong question of an ill-posed system of equations. And so, I mean, in many ways, we know that the representation of these processes in the models are imperfect, somewhere between imperfect and totally inadequate. And I think what we need to find out is where along that spectrum it lies, right? We need to have some kind of objective way. And the other thing that blends into this is the point that Sylvia was making, that it's, for many things, it's unclear how fancy the representation needs to be, right? And it's probably going to be different depending on which science question we're asking. So again, I think there needs to be some kind of objective arbiter that can tell us what's good enough. And again, I think CPE calibrated perturbed physics ensembles are the way to do this. most objectively. I mean, it's going to be in the framework of a model, but yeah.
So to sum up, your take is we actually don't know how well we need to know the microphysical process rates for worm ring formation, for collision coalescence, and we need to find out how well we need to know it.
Yeah, exactly. Yeah.
Okay. So this is Donny van Barahona from NASA. I do agree that PPs are a tool, a very useful tool to understand the sensitivities of a model. And that, I mean, the work that you're doing also is very important to understand which parameters are more significant and which ones are not. But at the same time, having a model with 45 different tuning knobs is a dire situation. I mean, we have so many tuning knobs in the microphysics, and you add the surface tuning knobs and the boundary layer tuning knobs, and then the radiation tuning knobs, we end up with a 500, probably 70 something tuning knobs. And at that point, probably we can just spare the physics altogether and work on that. So there must be a way to use observations or laboratory studies or some physical constraint that we can put to those tuning knobs and separate them between what we know, what we are confident that we know, and what we cannot really know because it comes from the interaction in the climate model. But the 45 or 50 or 500 seems a lot to just, it may look like we don't really have a model that is correct at all.
So I think, so from my experience, what happens is it's all relative. So all the parameters are important, but given the specified ranges of the parameters that we try to run in the PP, some parameters stand out. So this is kind of relates to my last slide. All your interpretations are conditioned on your PPE. So the parameters that we picked out that are important are conditioned on these parameters ranges and the other parameter ranges. So it's like you can zoom in infinitely, and you zoom in, it's still like an infinite space. So it's all relative is what I would say.
Yeah, I'm just worried that the more parameters we include, the less information we can get from those PP.
Yeah. So just something that your question brought up for me is, and Ken's question also is, it's easy to write a proposal where you're going to say, I'm going to put some extra complexity into the model, right? Because it's probably going to do something and you get some interesting results out of it. But every time we do that, that comes with a hidden cost, which is that it's going to become more difficult to understand the model. But I think this might be especially true for when we write emulators, unfortunately, because for simple parameterizations, we have parameters and we know how we can assess uncertainty by doing PPEs, right? But for emulators, we have bazillions of parameters now. So then what do we do? Okay.
When I look across the talk, something that strikes me is the role of regime. So we heard from Nicole about a polluted coastal regime from an aerosol perspective, and I think a couple of the speakers talked about more of a deep convection or RCE regime, and then more of a shallow cloud regime, maybe in your work, Johannes. And I wonder if you all had thoughts about how we put the puzzle pieces together when it comes to regimes. Something that's really appealing to me from a climate model evaluation standpoint is to make sure all the regimes add up to one. And so the weather state approach is appealing. Another appealing approach about the weather state pioneered by George Sliutis is that it also has an observational analog that's applied directly to the climate model. So they all add up to one, and you have an observational, a way to map that to observations. And so I wondered if, when we think about frameworks that span this work, that bring this work together, if I guess a question for all of you, if you think that how we bring the regimes together in the whole picture would be an important aspect of the framework, and if you had any thoughts about this in your work. Anyone want to bite on that?
First, I mean, I think of the global model as the thing that does this, I mean, kind of intrinsically, right? And I don't know if we have any real fundamentalists here who get up and say, why do we need global models anyway? But I think that's the answer for why we need global models, right? Because something needs to synthesize all the different regimes and the interactions across scales.
I guess a little more pointed, do you think that there is, that it would be helpful for, as part of a framework for drawing us together, that we have a shared framework, that works well across our groups for regime identification? Because if we all have different regime identification frameworks, if we can map on, if you think that's an important goal or just out of hand, not worth trying to pursue, too complicated, I don't know.
I think it absolutely is important. And I think what you did with Model E3 is actually the prototype for doing this the right way, right? Because Model E3 was tuned so that it reproduces things across regimes. And so I think if we're going to converge on something as a community, then my view from the outside in is that hopefully we do it the way that E3 did it.
Yeah. And a little bit, I don't want to call it disagree, but add another perspective in the sense, if you start with the global model, there are so many, from my point of view, being not a global model, I'm more like a process level modeler, so many simplifications already that, if your global model, your aerosol treatment doesn't have any size representation, then of course it won't be sensitive to size, right? Very oversimplifying stated. And so I wonder, it would be really nice from my perspective to have like a model hierarchy ready to go, because it is like this multi-scale process, right? And so, but making this model hierarchy consistent across, from the aerosol perspective, but I think there's an analogon in the cloud physics perspective, the representation of the aerosols and the clouds and also the spatial. I think these are the two things that really play a major role. And so then you can define regimes from the bottom up. That's maybe my main point.
Yeah,
we are certainly looking for this. If something doesn't matter, for high supersaturation in terms of aerosol modeling, well, then we don't need to worry about this for strong updrafts, maybe, right? But if it turns out to be very much sensitive in the low supersaturation regimes, then the shallow clouds maybe need to worry about that.
Yeah, I absolutely agree. I mean, we need some tool that tells us what is important for a particular science question, right? And it shouldn't take an entire career to come up with that tool. So if it's a model, if it's a model hierarchy, then it should be easy for people, the experts at each level of that model hierarchy, to talk to each other and to use each other's models, because otherwise we're never going to get the answers to the questions that we're after.
Yeah, when I first heard about PPEs, they were called perturbed physics ensembles. I'm not seeing perturbed physics ensembles in anything that's been discussed this morning, because they're not really addressing structural differences. Right? The example would be, you have a model that doesn't have an autoconversion accretion formulation. They've got a different type of formulation, doesn't really matter the details. How do you compare that with a model of autoconversion accretion? You just can't do it. So these PPEs are really addressing within one model, how can we make our model sort of look okay? But they're not really addressing how we can compare against another model. So how do we do that? And it's sort of, I was kind of inspired by Ken saying, yeah, we need more. It's difficult. That's why we're not doing it. It's really difficult because you've got to get together. The modelers have got to get together instead of, being in their own modeling centers. We've got to get rid of that model, right? So anyway, thoughts on that?
Well, so I think Hassan actually had an example of perturbed physics, kind of, right, with the GPL that has the minimal recipe. But I think, so I agree, this is a tricky problem. But I think that, so I know Duncan is working on this, Leighton is working on it, probably other people, other colleagues of Ken's, about how you can use perturbed parameter ensembles to figure out when you have structural incompatibilities and things like that. So I'm really not the right person to answer this question, but I think there are people who know the answers.
So I think it's like just you just gonna, where there's a new version of the model, you run a new set of PPE, and it's very likely you have some new interpretation on the parameter and output relationship in the PPE. So I think it is in a way it's very floaty. So you always end up something that's kind of unexpected. But what's important is the analysis on the PPE, because it explores a range of the parameters. So when you have structural errors, you know what variables you cannot emulate, and perhaps could guide you on the working towards it.
Chiu.
Hi, sorry, this is a little bit too tall. Okay, good. Yeah, so actually I want to comment on the things about step back and think about what we can do with the climate model. What we really can do without supersaturation and the updrafts. So many these climatic processes we are talking about, activation, condensation, they cannot be physically parameterized without supersaturation, updrafts. So, we rely on saturation adjustment for the condensation in vibration. And this is just one of the example. This is very important for the aerosol interaction, the start process, also the activation. So that is, we actually, if we are just trying to, get there and with the approach that the accuracy, we would never get the accuracy we need. But we can think about it in a way, what we can do is that provide the uncertainty range. So maybe that is what we look for the climate model. It's not a target at the accuracy, but a target at the sensitivity, which what kind of range we are in, and what's the climate would be sensitive to that range. I think that probably something just as an example as what really we can do within this community and what we can identify, which can move forward more, in more substantial way. Because otherwise we'll keep just parameterize those processes that we cannot actually get a good result. This is also come from my experience in the high resolution model, LES and CPM for many years, and then involved in the climate community just in the recent years. So, for me, I have a complicated feeling about the physical parameterizations in the climate model. We have this, even just, in the cumulus parameterization, you have very bulk crude representation on how much it will be detrained into stratiform. It's really so, I don't want to comment too much, but it is something which I would say it's so hard to get to the accuracy we need. Something to think about for this community. Thank you.
Can I add on this? This was a very good comment. And can I add on for some global modeler, maybe Johanna? Do you think if we are not about accuracy, but about the sensitivities, given the structural uncertainty that we have, can have confidence in capturing the sensitivity?
So, I think we will always end up with uncertainty, right? And the uncertainty might be larger than we like, and it might even be too large for us to address a particular problem. But we should be striving to make the uncertainty as small as possible, right? And part of that is figuring out whether the model is just structurally not suited. That's certainly part of it. But yeah, I think, and the other big part is we need to have the framework that lets us do that quantitatively and objectively.
We have an online question from Patrick. So We're going to unmute you and hopefully you can ask your question out loud.
Awesome. So I'm going to come back to this point about funding and how we bring all those pieces together, because I think I spent a number of years in the process studies model improvement panel with US CLIVAR, and this point came up a lot, and I'm sure Mike knows or recalls some of these conversations. And so, you know, there's a lot of aspects of this problem. And when I come back, I'm probably going to ramble a little bit, but when I come back to this, I think there's a key role here for our climate modeling centers, right? And so that's what I guess I'll have the panelists maybe comment on a bit to understand how can we better use those modeling centers in this, because you know, those puzzle pieces, all those puzzle pieces together, at least in my mind, come together when you develop the climate model and at these places, at the centers in particular. So, you know, we all know that the challenge here with funding PIs, when we write a proposal to wherever, oftentimes the budgets are way too small, right? And so that's one of the key challenges that I see, is that you know, the key people on these projects, you're only able to write single PI projects, right? And we really need to get across this. You need to consider like larger project, maybe more complex, multiple PI. So that's, I mean, one issue that we've talked about over the years. And then another thing that, you know, I think is something that we need to consider, and maybe this is things that we can talk about more in the discussion later on, but it also seems that the way it works at the funding institutions is that, you know, nobody wants to zero out any specific area, which I get, right? We don't want anybody to go to zero, but what that means is that all the funding that we have, which is limited, gets spread very, very thin, right? And so maybe this is a point where we can think about, as a community, identifying some specific tall poles where we'd really like to see kind of focused funding, so we can actually make good kind of jumps forward, right? Instead of being spread too thin, right? That takes, it's hard to prioritize like that, because in the end something might go to zero. So that's another thing I like folks to think about. So coming back, I'll stop talking now, but coming back to my initial question is, you know, how do we see and how can we better leverage the role of modeling centers in bringing all these pieces together? And is it something that's missing potentially, is the ability to bring in other PIs to do more residencies? I know it happens, right? Where we have folks come in and do residencies at NCAR or other climate modeling centers to kind of help communicate that knowledge. But is that a program that we can maybe bump up a little bit to help really maybe advance this? Just a couple ideas. Any comments? Thanks.
Yeah, maybe I'll add something to that. I think student training is probably an important component of that. I think, you know, as somebody who's learning how to train students, a lot of that training is sort of also easier done at a process level, where it's sort of like, this is the process that you're gonna try to understand. And I think, you know, also training the next wave of people in the context of like modeling centers, where they can get broader exposure to different kinds of expertise and people who know about the different components. I think, you know, that is also an avenue for using modeling centers that can be quite beneficial.
So I don't have much to add. I agree with everything that you said. And I think what's particularly sad is that we're not actually really asking people to do much extra work apart from just talking to other people. But when I try to do that, it ends up being frustratingly difficult. It's, you know, the project that does process understanding will say, well, that's interesting, but it doesn't fit into our objectives. And the project that does the modeling will say the same thing, and then it just never happens, even though the amount of work required is small and the payoff is enormous. Or, well, I mean, the cost to not doing it is enormous.
This is Hong Wei-Sun from University of Washington. First, thank you very much for all the great talks. I have a question for Nicole about the particles discussion. Is the internal and external mixture can introduce uncertainty when we estimate season. So I'm wondering, I may have missed that. Like, what's the theory or explanation behind that? Is that due to the activation process, like Kohler theory, like how it changed the curvature or the solution of the particles? Like what part?
Yeah. So what we try to quantify is how the assumptions about particle composition impact CCN prediction, and we do apply Kohler theory. So, you know, it really matters if the sulfate and the black carbon are together in one particle or if the two are separate, right? Even if the overall size distribution and the overall bulk composition is the same, that sort of mixing state degree of freedom can really matter.
Just quick follow-up. So would you also consider a structure with a particle like a curvature, or you only really consider solution?
Yeah. The particle size and the particle composition goes as inputs. We do not consider very well if the particle has layers or, you know, like the internal structure of the particle. We make certain assumptions about that. But certainly the curvature of the particle, we do assume spherical particles and what the particle is made of on a per particle level. That's what goes into our calculation of does it activate or not.
Nicole, can you try to speak into the mic?
Oh, did you not hear me? Okay, I won't repeat it now.
So first of all, Rob stole my thunder. That was a great question. It'd be nice if we had like some systematic methods for digging into structure. I think that's kind of what's missing. Maybe something that like Kara Lamb has done, looking into possible structure, or I don't know if like Bayesian model selection is really appropriate, but that's certainly something that's out there. But the question I will ask is, most of these uncertainty quantification things, PPE, stuff like that, they're kind of assuming that we can get the right answer, right, with this method, or we can get like a spread of answer, and we're like, okay, so we just put in this value and then we use it for the entire globe, and that's what we do. But our answers are not only wrong everywhere, they're wrong everywhere in different ways. So really, that's not a deterministic uncertainty. It's not like an epistemic uncertainty that we just get better at. It's something that is sort of stochastic, that's aleatory, that's irreducible given the structure of our models that we're trying to use. So are we really addressing that uncertainty? Is anybody like implementing that or quantifying that? I would love to hear.
And if you're sitting in the room and you do that, speak up.
So sometimes, like I said, sometimes the outlier, you saw that it's very deviate from your prediction when you do the validation. But sometimes it is from like not the globe, but some certain location that has give you very high values, and it relates back to some parameters. So what I've been trying to work on is to analyze the whole, like the PPE, not as just a global or regional. It's like trying to locate where this strange occurrence happens. Maybe that's kind of related to your question.
Okay, thanks. My question is for Hassan. So I really like the precipitation efficiency framework for looking at processes. I was wondering if you thought about, so I think it's typically defined, right, as P over total water path. What if, do we think we would arrive at any different understanding if in the denominator we had something like column water vapor plus moisture convergence? Systems across a hierarchy, whether it's an extratropical system or it's a mesoscale convective system or it's Eulerian grid box fixed, there's strong responses to the ongoing clouds and convection that will drive additional moisture increases that will change the nature of the clouds and the precip. So I'm wondering if we would arrive at any possible, if there's any advantage to looking at it as another alternate way of defining, precip efficiency, or if you think we arrive at the same answer and it's just related to how the typical way of defining it is, very linearly.
Yeah, it's a good question. So trying to get at the convergence of moisture is actually a way to try to get at the precipitating efficiency instead of the lifetime, because then in the denominator you can have a proxy for the condensation. So that would be really powerful. And I want to say there has been some work on this in the past. My colleague Kevin has looked into this a little bit, or at least has reviewed the literature of using water vapor convergence
Okay, thanks.
That way you have a rate divided by a rate, right?
Yeah.
Instead
Well, right, that's right. Yeah, yeah. Well, or you could formulate it as column water vapor, which would be in kilograms per meter squared plus delta CWV over some increment of time, right? And that would still be in the same units, where that delta comes from the moisture convergence multiplied by delta T.
Yep. Yep.
And so you could end up with still in the same units that you were using now.
Yeah, that would be really powerful. We should definitely explore that.
Thanks.
Zunju from Brookhaven National Laboratory. Yeah, just want to emphasize again what John has mentioned about this understand different pieces of puzzles, just from a remote sensing observation perspective. So I think it's really critical to understand this limitation of the observation before we use this to validate the model. So otherwise we are directing the model into a different way. So like take the most simple observation from precipitation. Like I also show this, see this figure in the talk that is warm green precipitation as cloud base maybe. So I think my understanding is that most of this observation from satellites using the cloud set, but we know that their classification of this warm green precipitation just the minus 15 dB is the threshold for the rain. And this maybe not give us a full picture, as we know that if we compare the satellite with a more sensitive ground-based observation, we know that they are missing a lot of the warm green precipitation already. So yeah, I think with the new launching of the Earth Care, it may be more better. It should be more better to observe the warm green process, but it's still it has some limitations, even though. So I think it's very critical for us maybe using the ground-based or like some other way to better constrain the satellite observation for the precipitation before we're using it for the model validation.
Yeah, I completely agree. And I think again, it's the importance of the two-way communication between the models and the observations, right? So the observations need to tell the models how the retrieval maps onto what the concept of the model is of this variable. But then also the model needs to tell the observation, this process is really important for the climate. Please design something that addresses this. Or this limitation of the system makes it really hard to compare models to observations. Can we do something about that? So it needs to be a two-way.
Oh, okay. Go ahead. Hi, Ute Herzfeld, University of Colorado Boulder. Has this chance to stand in line, so you don't have to sit around all day. And similar to the people ahead of me, I hold the opinion that no model's any better than the observations it's based on, and we work on improving observations from satellites, but also on model observation comparison. And that's why this is actually the type of conversation we came to have here. What wishes do people have in the modeling community? Like, what could you get out of satellite observations to particularly figure out reduction of uncertainty in aerosol typing or in aerosol existence in clouds, whether you have water clouds or ice clouds, and what type of horizontal or vertical resolution would you want to have? So I see certain processes like in the two talks that had to do with this range from hundreds of meters to hundreds of kilometers. So what would be your wish list? So we are actually specifically funded to make fancy math to get higher resolution of previously undetected aerosols and high clouds out of Calypso data and ISA2 data. And so we want to hear what the modelers would like to have. If we can do it, I mean, but it's good to have a wish list. So what do you think?
Anyone in the room is welcome to chime in too. Maybe it's better
I can
for a
start.
breakout.
Now I'm trying to speak into the microphone. Is that good? Okay. So from our perspective, being a modeler who really develops aerosol models, and we have this particular interest of how does mixing state evolve and how important is it? We really rely on, we have a hard time using satellite observations, actually. We can compare the end result, but if it doesn't match, it's very hard to pinpoint where did things go wrong. And for this reason, we need in situ measurements. which for aerosol, in the aerosol world, they become quickly very complicated because of the whole chemistry thing that comes into it, especially if you go into what are individual particles actually made of. But just to raise up an important hurdle right now, with these measurements, they are so specific and so sophisticated, and they have all their own angle and their own thing that they report, that it's really difficult to actually map them on some model results and even map them between the different types of measurements themselves. So they have a different diameter that they report. They look at different size ranges of aerosols. So to go with your analogy of the wombat and everything that follows from that, the analogy in the aerosol world would be the elephant. Depending on which corner you look at it, you see different things, and patching together the full elephant is something that I don't think we have achieved yet. So just to summarize, for us, it's really difficult, or maybe not that meaningful to compare the end-to-end products in aerosol optical depths or what have you, but it's important to do the in situ comparisons, because this gives you more constraints on the aerosol state. And there's a lot of difficulties and challenges associated with that.
We do need to start wrapping it up, so maybe just one more thought.
Yeah, but I mean, you don't need to necessarily compare the end results, right? You can take a process out and make an inverse model and compare it on a sort of regional scale, and then you can drive your parameters doing things like that. So then you have some kind of a regional patch between observations, and then you can better parameterize your variables, and then you can run that forward. So there are, I'm just sort of saying, there are sort of intermediate ways to do the model data connection without running like the full CSM at full throttle against all the observations. But no, I mean, I'd be happy to talk why you think we can't use satellite observations, or what we could do better.
All right, I think we're gonna wrap it up there, but I think that some of these themes are things that we can continue discussing in the breakout sessions this afternoon.
So now we're going to hear from our virtual poster presenters. And so these are participants that are attending the workshop virtually that are submitting a poster. Okay, our first presenter is Hideaki Kawai from Meteorological Research Institute.
Okay, so my poster is importance of minor looking treatments in cloud physics for GCM simulations. And for model performance and representation of meteorological phenomena in GCMs are of course controlled by physical equations and physical parameters. However, minor looking treatments are also very important, and that they include upper and lower limits in parameterizations and thresholds for enabling processes, and vertical resolution numerical method and sometimes bugs affect a lot for model performance. And this upper and lower limit in processes and threshold for enabling processes in various physical schemes, including cloud macro physics, cloud turbulence process, and cloud microphysics, and convection and turbulence. And these minor looking treatments are summarized in this paper. Okay, and I picked up several examples of the minor looking treatments. And the first one is the impact of conditionally disabling shallow convection. And when we turn off shallow convection scheme conditionally, so for example, only over the stable boundary layers, the low cloud cover increases a lot in these stratocumulus regions and also in Southern Ocean. So the shortwave radiation is also affected a lot. And the bottom panel shows the impact of lower limit of updraft speed for aerosol activation calculation. And in this case, the lower limit is very small, and the cloud droplet number concentration is small like this. However, if we set this lower limit of the updraft speed to 0.2 meter per second, the cloud droplet number concentration increases a lot like this. And the next example is impact of numerical method. And in this case, calculation for ice fall and conversion of ice to snow. And if we use not so good numerical method, the time step dependency is very huge like this, and this is scary. But however, if we use more appropriate and sophisticated numerical scheme, the time step dependency is much smaller. And also the impact of minimum height of permitting convective precipitation is very huge. So if we use a larger minimum height, the low cloud cover is much larger, and also the upward shortwave radiation is very, very much more than this 400-meter case. So please see our poster or Kawai et al. 2022 for more examples. Okay, thank you.
Next presenter is Vel Toll, University of Tartu.
So it is very challenging to quantify the causal aerosol impact on clouds. And this is largely due to the meteorological co-variability. So what could help are experiments, but controlled experiments are also associated with many challenges, both technological, also ethical, but it's possible to use natural experiments, so ship track-like experiments, where experiment-like settings happen without any intervention by a researcher. So here you can see MODIS satellite images of ship tracks in clouds on the top left, top right, a volcano track, bottom left, industry tracks, and bottom right, fire tracks in clouds. And then what we have been doing, we're using passive remote sensing data then to say something about cloud responses to aerosols using such polluted cloud tracks. Next slide, please. And I'm just showing here cloud water path, cloud fraction responses first for the precipitating backgrounds. And when we look at temporal evolution along these cloud tracks, so looking at cloud responses between polluted and nearby unpolluted areas downwind of the pollution sources using a few thousand of carefully hand-logged tracks, we see this gradual increase in liquid water path in pink and in cloud fraction in blue. But interestingly, in pink, you see there is this decrease in liquid water path right at the pollution source. So something like 10% decrease in liquid water path right at the pollution source, where we would really expect no change because it takes time for the liquid water path to change in response to aerosols. So this then refers to something strange. And if you look at the right non-precipitating backgrounds, there is really no change in cloud fraction, so I'm not showing this here, but change in cloud droplet effective radius in green and change in liquid water path in pink. So again, we see right at the pollution source this decrease in liquid water path and no clear gradual cloud thinning downwind of the pollution sources. So this here suggests that there could be a retrieval error in this passive remote sensing MODIS data. So some more careful work is needed to understand also this experiment-like settings, what should not be trusted blindly, especially relying on remote sensing. Thank you.
Our next speaker is John Lundstrom from the University of Illinois Urbana-Champaign.
So our goal is to move beyond the simplistic satellite retrievals of vertically integrated quantities like liquid water path or optical depth and retrieve the full 3D distribution of cloud optical and microphysical properties. So how can this be done? Next slide, please. So we use atmospheric tomography with 3D radiative transfer, or AT3D for short. This algorithm takes a state vector, which is a 3D representation of the cloud optical and microphysical properties, and it fits this to a set of measurements, which are multi-angle passive images. And it does this through the use of a 3D radiative transfer model, which maps the state vector to the measurements. We estimate a solution by minimizing the cost function, which is the residual between the measurements and the forward model and the atmospheric state. And to form updates to the state vector, we use the gradient of the cost function, which involves this Jacobian term, which is boxed at the lower part of the screen. This is quite challenging to Levis in 2015. And Jesse Leverage has shown that this approximation is good to within 12% air for typical cumulus clouds over ocean. Next slide, please. So in this study, we do a case study using a multi-angle imaging spectroradiometer applied to a scene from the CampX field campaign. So I direct your attention to number 1, where we can see an overview of the scene here. Overlaid, we see the NASA P3 flight tracks. And then we do our retrieval in the red boxed area. So then number 2, we see Miser's 9 view angles, which we supply to AT3D along with a set of parameters in number 3 to retrieve number 4, the volume extinction coefficient in these 3 dimensions. And as I mentioned, AT3D is an iterative solver. So we're seeing the converging solution here of the extinction coefficient field. We can supply this output to the forward model to see synthetic multi-angle images and compare this to Miser. And we see that it matches pretty well. And finally, I mentioned that we're collecting in situ measurements of the drop size distribution, so we can derive extinction coefficient from that and compare AT3D output to in situ measurements here in number 6. We see that although it's not a one-to-one comparison, AT3D does plausibly well. Next slide, please. So finally, from this experiment, we've learned a couple of things. First of all, we need a high resolution imager to resolve the small scale variance that clouds have. And then second, it takes 7 minutes for Miser to acquire its 9 view angles. Clouds can and do evolve on this timescale, and it poses challenges for the tomographic retrieval. So a constellation of simultaneous multi-angle views will also be important to go forward in the future. Thank you for listening. If you have any questions, please feel free to reach out via email.
Thank you so much. Our next presenter is Declan Finney from the University.
Hi. So I've made a change from my abstract title to focus this poster on Anvil Cloud albedo specifically, and this was motivated by the recent work that's already been flagged earlier in the session talks, where the McKim et al. Papers highlighted that probably we need to move on our thinking from the original review by Sherwood et al., where we were thinking that the area feedback of high cloud could be quite negative, and instead there seems to be the sort of biggest unknown is in the albedo response to warming. So I'm working on the DCMEX project, which went and took some aircraft measurements of numerous deep convective clouds in New Mexico. Got a lot of measurements there, and I'm using the UK Met Office unified model to simulate these cases and understand what microphysical controls there might be. Next slide. So here I'm showing what the a number of cases are the black dots, and then along the x-axis is several different experiments, and the y-axis is the percentage anomaly relative to the control experiment. And we show that, well, basically we use the observations to kind of define some useful experimental ranges and test them here. So when we double the droplet number, and also when we increase the IMP numbers, we see significant increases in the high cloud albedo in both of those cases. And if you go and download my poster, then you'll see that there are kind of different routes by which these two processes affect albedo, and you can find out more at that poster. Just to link through to a couple of other posters you'll hear about, there's three of us from DC Met presenting, so Alan Blythe will talk more about the observations in the next talk, and Meng Sun later on will talk about some tropical work. So thank you very much.
With that, we'll hear from Alan, and it sounds like it's a continuation of the previous work. So Alan's from the National Center for Atmospheric Science, University of Leeds.
Yeah, thank you. Yeah, as Declan said, our poster was about the deep convective microphysics experiment. So one question we're asking is, how do microphysics processes in the mixed phase region affect the anvil cloud albedo, as Declan just described, and there's more information in his poster. And also we wanted to test and if necessary, improve the Met Office microphysics module, Kazim. And we've already made some improvements actually to the model. So and then apply that to the tropical deep convection, which Meng Sun will talk about and is in her poster. So the project was over the Magdalena Mountains in central New Mexico, where we've done some measurements before. Dave Raymond and others, and myself was involved in 1987. We took the FAM aircraft, and the aircraft made passes through the ascending tops and later stages of development. This diagram suggests here the clouds were anchored to the mountains. There were measurements of IMP, aerosols, and cloud microphysics on the aircraft, and also at aerosols and IMP at Langmuir Lab, with a couple of radars, and also using the NexRad radar. And the satellite information is incredibly useful. We also had a couple of ground-based time-lapse cameras, which gave us a great perspective of the developing clouds. There were 17 cases with varying environments. And one of the pieces of the jigsaw that we had were these different models, the UM with Kazim, as Declan said, and also CM1 and also a parcel model. Next slide, please. One of the early results that we have is from the measurements of the IMP. It says one of the few combined measurements of IMP and primary ice in convective clouds, and it resulted in a new parameterization in Kazim. It's quite tricky determining the concentration of primary ice, and what we're trying to do is look at the top of the cloud as indicated by this forward-facing camera there, and using the HVPS, which has this highest sample volume, determine if these images are ice or not, and then go up to the next level and repeat. So as far as we were able to determine, the first ice was around -12, -13 or so. And there are more early results presented on the poster. The right-hand curve here are the IMP results gathered during the project. Thank you very much.
Thank you so much. Our next presenter is Luis Ladino from the Universidad Nacional Autónoma de Mexico.
Hello, everyone. Thank you very much. So today the idea is I would like to show you a little bit how we are trying to understand how important are the regional IMP parametrizations compared to the global parametrizations. Next, please. So in order to do this, the first thing that we did was to develop and to use our droplet freezing technique to measure the IMP concentration along Mexico, so under different air masses, biomass burning, mineral dust, marine aerosol, urban particles, and so on. And then we get the figure from the top left, where we have the IMP concentration as a function of temperature. And once we got these in situ measurements, we developed some parametrizations, and you can see in the bottom right panel, where we can have different type of expressions, mathematical expressions. Some of them are exponential, some of them are power law. And then the idea is how to get this mathematical information to put into the Wolfgang model. Next, please. And then in order to understand how important are the regional IMP parametrizations, we select a case study. Our case study took place in Mexico City in May 2019. In May 2019, we have an extreme pollution event, as you can see in the figure from the left-hand side, where you can see in the yellow diamonds the 99th percentile of the PM2.5 concentration, and in the red diamonds you can see the PM2.5 concentration, the maximum values that took place on May 2019. So it is clear for us that we have a huge air pollution event at that time of the year, thanks to the biomass burning emissions around Mexico City. And at the same time, on May 15, 2019, we have an unusual Graupel event, as you can see on the picture, this soccer field that was covered with hail. So this is very unusual for us. We are in the tropics, so we don't have snow, we don't have Graupel very often. So we wanted to see how the new parametrization will behave when we incorporate it into the into the WRF model. Next, please. Next, please. So then here on the top figures, we have the vertical cross section, and then of the precipitation event that we tackled that day. So you can see, for example, on the top panels that hail didn't reach the ground. So we can see that they were Graupel at higher altitudes on the reddish colors, when we have IMPs on the left-hand side, and when we include IMPs from Paul Demott parametrization. However, as we can see, we saw Graupel at higher altitudes, but we didn't see it at the ground level. However, when we include the regional parametrizations at the bottom panels, Mexico City parametrization, Mexico parametrization, and biomass burning parametrization, we were able to get Graupel at the ground level. So here we can see that the local ground-based parametrizations are very important to improve the performance of this regional climate model in order to understand or to check these meteorological phenomena. Yeah, thank you.
Next, we have Luis from ECMWF.
I'll make it short. I just have this one slide, so should be fine time-wise. I'm a PhD student at ECMWF and at the University of Cologne, and my project focuses on mixed phase clouds in the Arctic in the ECMWF model. So it's a weather forecasting model. And has a comparatively simple scheme compared to many climate models. So in the project which I present in the poster, we use data from the observational campaign, from the Mosaic campaign, which was quite exceptional. It was the ship was drifting in the sea ice for 1 year and was collecting data from a place that's usually quite data sparse. Now we use these observations to evaluate the model, and we evaluate short forecasts. So day 2 of forecasts and videosons were simulated, so we can expect the model to be quite close and really evaluate the errors from the parameterizations, the ones that grow quickly. And yeah, the evaluation showed that there were seasonal dependent biases, which were kind of known from the campaign 10 years ago already. Not much progress there. And we see that there is an underestimation of liquid containing clouds, which we should see in the blue lines in the middle plot. And yeah, what we did then is that we developed a single column model set up to test sensitivities to the parameterization. At the moment, it's not dependent on any aerosol concentrations, but just temperature dependent, the processes. And yeah, when we use the parameterization from the mod 2010 and make it dependent on aerosols loads that were observed, that's actually enough to increase the liquid water path in the model from overestimation to overestimation. Yeah, and that suggests that we might should make the microphysics aerosol dependent in the CMWF model. Thanks.
Next, we have Ross Herbert, also from the University of Leeds.
Hi, everyone. The post I'm presenting is looking at improving the simulation of IMP concentrations, and we're doing this using a new long-term observational data set from PINE instruments. And the kind of key aim with this is if we can constrain or reduce uncertainty in primary ice production by getting the modeled IMP concentrations right, then that's probably an important key process we can actually constrain in cold phase cloud microphysics. Next slide, please. So we're doing this using a new global database of automated long-term IMP measurements. These are all using the PINE instrument, which does these automated measurements, different temperatures. And we've got lots of campaigns. So we've got no instrument-to-instrument variability, uncertainty, or differences in methods. So it's quite a robust method or collection of data. And they're also for over years, some of them months to years, which is kind of unprecedented in terms of actually being able to have a time series of IMP measurements to evaluate our models. So we're using this to compare to simulations using the UK ESM model, which has interactive aerosol from GLOMAP mode. Next slide, please. So this is just demonstrating what we're finding. So this is 3 different campaigns showing the time series of IMP concentrations. And the red is just showing the simulated time series. And it really demonstrates that without even tuning the model, just putting our best parameterizations for IMP concentrations in, we're able to get some of the long-term variability and even some of these really short-term variability. So I think we were quite surprised at how good we actually already can do these kind of things. And we can't do this without the measurement database that we're using here. Next slide, please. So to summarize, on the left here, that's just showing using all the different PINE measurement campaigns, comparing against the model. It's just showing the median bias against temperature. We want to be on that 0 line there, but most of the data does fall within about 1 order of magnitude, which is considering IMPs vary maybe up to 3 or 4 orders of magnitude at every temperature. This is a pretty good start, and we're really starting to actually be able to simulate these global distributions of IMP concentrations. So we're very happy, but there's temperature dependence, and this gives us some future direction. On the right here, just showing that we can back out the parameterizations that would reduce the uncertainty further. And so this is the kind of future focus of our research. So come and have a look at the poster, ask me any questions. Thank you very much.
And our final presenter for the day is Meng Gao Sun from the Department of Earth Environmental Science, University of Manchester.
The topic is the impact of secondary ice production on tropical deep convective clouds in actual thunderstorm. And this work is part of the DCMX project, which has been produced by introduced by the Dedekind and Alan before. And for the background, the ice particle concentration in collective clouds are observed to be orders of magnitude higher than produced directly from the ice nucleation particles, and this reveals the existence of the SIP in addition to the primary ice nucleation. So the ice particle enhancement may have significant effects on the cloud dynamic, precipitation, and cloud radiative properties, further impacting the surface energy budget and the hydrological cycle. So our study aim to introduce SIP processes, including the RAM splittering, ice and ice crystal breakup, and droplet shattering during rain freezing into the unified model, which in which the CLIVAR module is part of the macrophysical module of the unified model. And secondly, we are going to investigate the effect of different SIP on the macrophysics and dynamic of a simulated Hector storm. In this research, we use the MetOffice unified model, and we use the CLIVAR, which is a two-moment macrophysics scheme in this model. And this scheme consider different macrophysical processes, and we consider different SIP in our macrophysical module. And we can see the results, which I want to talk about most is that our simulated results are more consistent with observations, and we compare the time height plots of the CFAT, which represents the fraction of radar reflectivity larger than 10 dBz. You can see in figure 3, we can see that after all SIP considered, the CFAT is much more consistent with the observation, and we then compare the macrophysical properties after considered the different SIP processes. The figure 4 is the mass mixing ratio and number concentration, and the mean mass radius of different hydrometers. We can see that after all SIP is considered, the number S concentration is much more higher than the other experiments. So in the future, first we need to do more sensitivity studies to examine whether the current SIP schemes produce too much ice, or if the conversion of the ice crystal between categories lead to this phenomenon. And secondly, we are going to determine the best representation of the SIP processes and rates on the dynamical processes, precipitation and radiation in tropical convection, etc. I think that's all. Thank you.
Thank you so much, everyone. Let's give all of our virtual poster presenters another round of applause.
This is what I am doing, but within the context, what I've identified as empirical relationships to predict the number of ice nucleating particles. And as a chemist, that's a little bit unsatisfying. You know, what does that mechanism look like? So that can be positive in terms of it's, you know, computationally not too expensive to implement this empirical relationship and this parameterization. But again, as a chemist, that can be problematic. And it's problematic because we don't currently have a mechanism to predict the ice nucleating ability of any aerosol. And in my group, we specifically look at organic aerosols, and I want to highlight 3 key importance of our current inability to predict the ice nucleating ability. Because, for example, we have a lot of forest fires. Their intensity is increasing. They are penetrating really much higher up in our altitude. And so understanding how the organic molecules are nucleating ice is important, but we currently don't have a way to predict that. The other context is a contrail formation. So as the aviation industry is moving towards using lubricants and sustainable aviation fuels, we are injecting new molecules into the atmosphere, into our aerosols. And of course, the context of geoengineering and putting aerosols that have chemical properties that we have not studied yet. So now this is kind of the problem and the issue that I see and that my research group is wanting to address. So before I say that, I will also add that in preparation for this workshop, the organizers sent us kind of a guide for our slides. And they had this amazing analogy of penguins being important for climate. So I thought it was so good that throughout my talk, if you see a penguin, that's my main message. So I'm going to use their analogy with my penguins, and it seems like there's an animal theme going on. We saw some wombats this morning. So yeah, when there's a penguin, it means it's important. And so really what I'm trying to kind of give you an understanding is that my research program here at UBC is looking at atmospheric chemistry and trying to develop a predictive tool to better predict the ice nucleating ability of organic matter. And what I tell the students is that essentially, you know, I want to know what's the list of questions that I need to ask about the material that you're bringing to be able to predict their ice nucleating ability. So in my lab, the way we do that is we have two approaches, and I have to define these top-down approaches and bottom-up approaches because as a chemist, they are different than as a modeler. And I want to also highlight Team ICE in my group, both the alumni and the current members, Paul, Emilie, and Emily. So for us, what a top-down approach means is we take the aerosols from the complex atmosphere and we bring that into the lab. And then we can do treatments like filtration, heat treatments, oxidation treatments, and then separation to understand what molecules were responsible for the ice nucleating ability of the whole. So that's what we call the top-down approach. And what we call the bottom-up approach in my lab is really then, as chemists, using single molecules and then building complexity as we go. So I've got pictures of molecules on my slides. So these are lignin molecules from biomass burning, cellulose also from biomass burning. And then I've got some proteins, and the protein here is ENA-Z, and it's one of the most efficient ice nucleating proteins that we know. And we don't really know why. What is so unique about this protein that makes it so good at nucleating ice in supercooled water droplets? So the idea here is that we can combine these two approaches and hopefully come up with a mechanism that is consistent of the top-down approach results and the bottom-up approach results. And so what that practically looks like in my group is we've looked at different organic matter, so whether that's from dissolved organic matter from rivers or swamps or forest fire or barbecue fire, and also looking at soil and the complex organics that are in soil versus building instrumentation and using analytical chemistry and material science tools to kind of build up our understanding. So what does that look practically in our lab here at UBC? So this is our ICE lab. It's a dedicated space for our ice nucleation research. And what you can see is a drop freezing technique. We call this FINC. We have a tensiometer that's been retrofitted to look at suspended supercooled droplets. And we also have a homemade cryomicroscope to allow us to look with high-speed cameras at nucleation in real time. And another key component that maybe if you're not an experimentalist, you may not appreciate is this big piece of equipment in the middle. And this is a laminar flow hood. And this is really a key instrument because nucleation can happen from a lot of impurities. And so we are very careful with how we prepare our samples, how we manipulate our samples in a laminar flow hood to make sure we're not incorporating any impurities in our system. Okay, so how do we measure aerosols? And this is not specifically from my group, but from the community of ice nucleating particles, is there are online measurements. And these have a lot of advantages in being able to deploy to the field and look at these measurements in real time. So there are instruments called continuous flow diffusion chambers. So this is an example of spin. And there are expansion chambers. I have the expansion chamber at KIT here, as well as the Pine chamber that was mentioned also by Rob in the virtual poster session. And these are able to look at ice nucleating particles in situ, whether that is forming ice crystals within the instrument or within the expansion chamber, and then extracting out information from those particles. There are also offline measurements that I want to compare to, and that includes these bulk solution measurements, these drop freezing techniques. I've highlighted a couple of papers, 2 of them that I've been involved in working. And then the last one, so the 2021 is the one that we have in my lab at UBC. And basically what this entails is pipetting bulk solution of either proxy or captured aerosols onto either a plate or a tray, and then looking at the ability of this material to supercool, and then noting the freezing temperature of those droplets. Now, if you look in the literature, there are over 40 of these instruments. These are not commercially available instruments. They are home built. So there is a big community effort to making these instruments. But there's the issue that they then have all very different characteristics and make it difficult to compare samples. Now, there's been some really nice efforts in these intercomparison studies to basically send to all of these instruments very similar material and try to look at how the spread of the ice nucleating material is, and it's usually actually quite large. And so what happens is these instruments have different droplet sizes, and that's a key point. They'll have different number of droplets per experiment. They'll have different surfaces and interfaces, and I hope to tell you today that this is important because some of them will have a plastic water interface like our instrument, but some of them will have a oil water interface, some will have a solid surface, some will have a coating. So those interfaces, I think, really matter and hinder our ability to extrapolate the freezing temperatures that we see in our instruments to what is happening to the real atmosphere. And then same with droplet shape, because there can be domes when the droplet is sitting on a surface. In our system, it's actually a cone shaped, and this is not what we have in the atmosphere. And then finally, because of all of these different setups, we have different water backgrounds. Okay, so penguin, notice here is that this is a disadvantage. And I think is slowing down a little bit our understanding of ice nucleating particles because we have so many different systems. And on the topic of water backgrounds, I want to highlight that in this field, there are multiple papers looking at specifically how to keep our systems as clean as possible and as reproducible as possible. So there's been some work by the group of Ryan Sullivan as well as Paul DeMott in trying to really look at protocols to try to stay as clean as possible. And we've also looked into and suggest that heating trays can be very important in lowering the backgrounds of our system. And what this is showing here is a frozen fraction as a function of temperature. And you can see how terrible the frozen fraction is of just clean water, just because it's an untreated tray. And we still are thinking about this problem in my lab, and we have an ongoing work looking at this particular plastic surface to water interface. And we found that if we can coat our surfaces with fluorophel, which is another molecule that is very hydrophobic, then we can try and avoid some of these higher backgrounds that we're seeing. We've also made sure that what we've noticed is that using glassware can be very problematic because you can have small pieces of glassware that can then act as ice nuclei. That was a whole summer for us spent on this problem. We think it's important to pay close attention to the material's composition, looking at imperfections in the tray. We have microscope images to highlight that, how these trays are even printed by the company. If it's polyethylene can have an impact. And so we're saying that maybe coating a tray is one way to harmonize these issues. But we are at this US CLIVAR workshop, and so I can think big. And so here's another penguin slide. And so I have a dream instrument that I want to share with you all. And my dream instrument would have spherical suspended droplets. We would only have an air-water interface. We could be looking at hundreds of droplets simultaneously, and we could use with a wide range of volumes. So I don't have an answer to this dream instrument, but I can tell you this is something that my group's been thinking about. So maybe to check in with us in a couple of years and see what progress we've made here. But in the meantime, I do want to tell you about an instrument that has helped us really understand and study the air-water interface of single droplets. And again, this is because we're interested in where in the droplet nucleation is occurring. So this is work done by PhD student Paul Bieber in my group, and he built this cryomicroscope that had high-speed images, or a high-speed camera. So the high-speed camera is at the top of the objective, and we're looking down, and we're seeing the droplet from the top. And the droplet is then squished between two slides. And I can tell you we've done a lot of control experiments, and I'm happy to talk to you about those to make sure that what we are seeing is always due to the material in the droplet and not the slides that is sandwiching the droplet. And so we had a high-speed camera, and so I want to show you some of these videos. Also because the session title is called Can We Observe Microphysics? So I'm going to show you some microphysics. Okay, so here we have docosahexaenol. So this is a molecule that has a hydrophilic head and a hydrophobic tail. So we call it a surfactant. And so we expect the docosahexaenol to be at the interface of this droplet just because of its chemical properties. And so then we expect the ice nucleation to occur at the interface. And lo and behold, this is exactly what we see, nucleation at the interface. If we go over to birch pollen extract, this material is now very soluble, water soluble. And so we don't expect to have a surfactant property. And so we don't expect this material to nucleate at the air-water interface. Rather, it's going to be in the bulk. And this is exactly what we see. We see nucleation in the bulk. And then we turn to this ENA-Z, this bacterial protein that is one of the most efficient material that we know. And we hypothesized that it would be behaving at the interface. And indeed, this is what we see. Now, this material is nucleating at -5 degrees Celsius. So the ice propagation is much, much slower. But we do see that it was nucleating at the interface. Now, to get statistics, Paul needed to rerun these experiments over and over and over and over and over again. And so let me show you now. These locations is what Paul was using as his primary data. And so now we have these target plots. And so we've divided the droplet volume into 5 different volumes. And what we see is that the normalized nucleation frequency of the docosahexaenol is very clearly at the interface. And this is beyond just a random statistics. This is really an enhancement at the interface. And we do not see this interface at all Is everything okay? I heard some voices.
2 minutes left.
Yes, okay, thanks.
Sorry about that.
At the interface here, but we saw nucleation happening at the bulk. And then for the proteins, what we see is there is a very clear enhancement happening at the interface. And so we did a lot of different tests to try to purify these proteins and then add surfactants and manipulate the space. And what we came up with is this particular diagram. It's an air-water interface with ENA-Z as our orange protein here. And depending on where it is located in the droplet, we're going to see different aggregation mechanisms, and that's going to dictate where the material is going to nucleate. And so what I want you to highlight is the importance of these hydrophobic interfaces, and that they are chemical interactions that are driving this aggregation. And my penguin slide here is that we've been thinking that how the droplet is freezing can also impact secondary ice processes, and whether the ice is or the droplet is freezing from the inside out or from the outside in can matter. So in the last minute that I have, I just want to tell you that we've been thinking a little bit more about this process of aggregation, and Paul's most recent work has shown that these different organic material that we do find in the atmosphere have actually the ability to form particles in solution without us doing anything. So once they are in solution inside the droplet, they can form particles. And we think that that can be really important in predicting their ice nucleating ability. And this is what Paul was able to extract using this NTA analysis, the mean hydrodynamic diameter. And we're kind of surprised, but we're also kind of excited that there seems to be a correlation between this hydrodynamic diameter and the freezing temperature of this setup. Okay, so I will leave you with my last slide, and this is my last penguin slide. Thinking about cloud microphysics, heterogeneous ice nucleation in particular, and the gap in knowledge that we are currently using empirical relationships to predict the number of ice nucleating particles because we don't have a current predictive model. So my take-home message, I'm a chemist, so take it with a grain of salt, but chemistry can matter. And we've been looking at aggregation of molecules at hydrophobic interfaces, size and chemistry of aggregates, and again, the hydrodynamic diameter as a potential important question to think about when predicting ice nucleating ability. So here's my scientific wish list in the spirit of this workshop, thinking about this like dream instrument that is free of interfaces and free of non-natural interfaces, I should say. Thinking about databases of ice nucleating material so that we can start and think about predicting this material. And ultimately, I want to be able to know what are the key questions that I need to ask to be able to predict what the ice nucleating ability of any new material might be. Once we know these questions, then we can think about how to implement them in a model. Which questions are going to be important? Which questions should we prioritize? And hopefully we can add that knob within the climate model. Okay, so my group and I from Vancouver would like to say hi, and I will leave it here for questions. Thank you.
Thank you, Nadine, for a fantastic talk. We're going to move on to the next talk given by Christine Chiu from CSU. She's going to deliver a voice from the cloud remote sensing communities.
All right, thanks very much for this opportunity to talk about our work and the challenges that we are facing. And I just have a few notes to make before I start my talk. So first, I need to add aerosol layer because Masa wants me to cover that part as well. Secondly, I have to introduce my own work, our own work, because it's just more effectively to use our own retrievals to highlight some problems. I don't mean to be exclusive. It's just I think a workshop is focusing on the problem and how to move forward. So I hope you don't mind. So I'd like to thank my co-authors. It's quite hard to see. Postdocs and students from my group, and Jesse is here somewhere. Jesse is there. So if you have any questions, please feel free to talk to him. And also my colleague, Peter Yang van Leeuwen at CSU, and also collaborator, Graham Feingold and his group. So I'd like to start my talk with this slide that everybody know, very familiar with. And I highlight two bars there. The first one is the aerosol directed radiative forcing. The second one is the aerosol cloud interaction. Many of you have been working very hard to reduce the uncertainty due to aerosol cloud interaction. But here in this talk, I'd like to draw your attention to the best estimate of aerosol direct radiative forcing. I will explain it to you later because I think we may need to revisit the estimate. We have seen this one already, so we know we have the large uncertainty in radiative forcing, but also cloud feedbacks. So I will just skip that. The key point is we still have a larger uncertainty in cloud feedback, both in warm clouds and tropical envelope cloud area. Okay, if you read the paper in the end, the improvement will rely on our improved process level understanding, and I think that's why we are here. So to reduce the uncertainty in the forcing and feedback, satellite observation has been used a lot to constrain the estimate. I just wanted to take this opportunity to highlight again that a lot of the satellite cloud products, not a lot, basically most of them, are really based on the 1D radiative transfer. So it's not new, and the error due to the 1D radiative transfer can be large. And it depends on the solar-emissive angle and the cloud inhomogeneity. And this one is just a highlight, just using two cases from the Japanese group. They try to incorporate 3D radiative transfer in the cloud retrievals. And then so you can see the top there in the red square. You can see if you use 1D radiative transfer, the cloud optical depth error can be 70%. And cloud effective radius can be 50%. But if you manage to incorporate the 3D radiation transfer, then we can reduce 2 to 3 times in the cloud, the error in cloud optical depths, and perhaps 10 times in the cloud effective radius. I just wanted to highlight here is because this is an outstanding issue. Everybody knows that, and I think everybody forgets about that. Just because it sometimes works doesn't mean it's okay. Just like a relationship, where you stay if it sometimes works. I guess we all do, right? Sorry, lost my share. So the thing is, how do you go to how are you going to incorporate 3D cloud radiative transfer? 3D radiative transfer. If you don't have a 3D cloud fields to start with, you can't really do that. So we actually still have a very limited 3D cloud observations from the ground, and I would say none from space. Maybe this is a strong statement, but I just wanted to highlight the problem here. So let me focus on these to the outline of my talk. So first part, I will focus on the aerosol part to show you how we advance the aerosol observations on no man's land. Then I will show you the challenges in observing 3D cloud microphysics, and also the challenges in observing concurrent species in warm cloud and ice-containing clouds. So in case you are not familiar with the aerosol remote sensing, I just wanted to sort of briefly explain how that works. So typically we predefine some aerosol models. You put into the 1D radiative transfer, you calculate the reflectance that satellite is supposed to measure. Then you have all the calculation ready. You grab observation, take a look, compare them. Then you can sort of estimate the aerosol property to see which one match the observation best. And we call this so-called lookup table. The thing is, you will find that almost like 25% of the satellite pixels, you won't find the answer Why? Because the 1D radiative transfer, you will see the observation is, you can't use it a 1D radiative transfer to explain your observation. What do I mean by that? And here is just a statistics from the MODIS measurements from Tamash's paper. So let's just bring MODIS reflectance by the distance to the nearest cloud as the axis level shows. So 0 meaning right at the cloud boundary. The right-hand side 20 kilometers, you can consider a pixel that is very far away from clouds. Y-axis there is the reflectance compared to the pixel, the pixel you observe that far away from clouds. So you can see when you approach to cloud boundary, the reflectance actually will increase. And this enhancement is due to many reasons. Some are real, like the aerosol hygroscopic growth, new particle formation, chemical processing in clouds, but some are actually artifacts. For example, the undetected subgrid clouds and also 3D cloud radiative effects. Among these 5, the 3D cloud radiative effect is the biggest source of the enhancement of the reflectance, which is artifact. So in order to retrieve the near cloud aerosols, you got to manage and handle the 3D cloud radiative effect. So what we did here is we developed the machine learning techniques and then trained the reflectance using the 100-meter LES output. And more importantly, we did include the 3D radiative transfer in this training data set. We also include the aerosol hygroscopic growth when we calculate the aerosol property. I'm not going to give the detail. You are welcome to read our papers. But here I just wanted to show you using the testing data set. We sort of evaluate what the uncertainty the aerosol retrieval should be. So this scatter plot is predicted versus truth. And you can see the uncertainty is about 0.01 plus 5% AOD, which meets the expectation for the pre-launched satellite mission. So here just to show you sort of a testing data set. What does it look like then? So here I'm just to show you one example to compare MODIS dart target 3 kilometer product. That's left-hand side from the dart target and right-hand side is our retrieval. The white areas meaning either cloudy or near clouds that reflectance is too high for MODIS to do any retrieval. And using our machine learning retrievals, you can see we do fill a lot of gaps there. And also near clouds, you can see the aerosol uphill depth is enhanced. So once we sort of feel like our retrieval method works, then what we wanted to know is, does it matter to do the near cloud retrievals in terms of a aerosol direct radiative effect? So we pick up the flowers, gravel, sugar, and fish. I know some of you don't like this kind of a separation, but just bear with me. It's convenient for us to really just see what's the impact. So we do the retrieval and calculate the aerosol direct radiative effect and see how much get enhanced. The results is somewhat surprising to me, but we'll see if it's surprising to you. So we found the flowers in the flower scene. If we count near cloud aerosols, the direct effect will get enhanced by 33%. Gravel is 14%, sugar is only 11%, and fish is about 42%. So before my students send these values to me, I thought gravel will be the highest because of all the precipitation, evaporation, the humid area. It turns out that the flowers and fish has a bigger play here. The reason is the enhanced radiative effect is determined by 2 things. The first thing is the contrast in humidity between near clouds and far away from clouds. The second thing is so-called the cloud halo width, meaning around clouds, you have a high humidity area. How wide that is actually is important. So it turns out the flowers has the biggest contrast in terms of the humidity between near cloud and far away from clouds. But the cloud halo width is narrow, so, and the fish has a smaller contrast compared to flowers, but the cloud halo width is much wider, and it turns out the fish has the biggest effect. So 30%, 40% is not small, and that's why I would think the community probably should really start thinking to count near cloud aerosols in the IPCC report. So I'm going to switch gear to talk about 3D cloud observations. And we are not the only group who have been thinking about 3D cloud observations. But what we do approach this problem is slightly different from others. So people have tried to construct the 3D cloud fields using A-Trend, for example. What they did is we compare the space-borne, the short-wave reflectance from MODIS, and combine the cloud set, for example, the radar reflectivity as the curtain shows there. In order to reconstruct the 3D cloud fields, then you need to have the radar reflectivity. So what they did is a so-called match-up donor and recipient. So what I did is grab the cloud set along track radiance and compare to the of nadir pixel radiance. So if the radiance is sort of close to each other, then we assign the radar reflectivity from a long track to of nadir pixels. So by doing that one by one, then you will have a 3D fields of a radar reflectivity and the MODIS reflectance to constrain your cloud retrieval. And by the way, this is what EarthCare is going to do. So, but what we are going to do differently is once we construct this one, then we will incorporate the 3D radiative transfer during the retrieval process, because without 3D, the 1D retrieval is going to have an error. And we are going to use the so-called particle flow retrieval framework. And why that is sounds fancy, but the key advantage of that method is really all about uncertainty. You can ask Jesse, we are trying to define if we do that properly, and he told me we need to take 25 days. We will see. So the particle flow really provide a complete posterior PDF of a retrieval, even for the nonlinear system. That's what we need. So let me use the cartoon to show you what that is about. So say we use the 7 particles, and if you like, you can say that's an ensemble member. And so you have a first guess that you start to iterate and update the retrieval. So the first particle may text quickly to converge to one solution, and the other particle may text slowly and then converge to a different solution. You run many particles, many ensemble members, and then take a look at what they end up with, and that is how we define posterior PDF. So in this method, we have 2 major terms. One we call the attraction terms. You can see the attraction term put some particle together and put another group together. We also have one term, so repelling term, that makes sure the mode are not, all the particles not going to collide to just one mode and separate properly, so we can define the coverage of a posterior PDF nicely. So this is sort of the essence of the particle flow method. And let me just show you, does it work? So we apply the particle flow retrieval method to one of the EarthCare test scene. And so that's a big cloud, but because right now it's still quite expensive, let me just show you one example that orange box is going to do. That's the cloud we are going to retrieve. And then the blue lines there show that you can assume that's a cloud set along track. That's where you will have an exact radar reflectivity to work on. So here is, I'm just going to show you 2 things. One is along track, just along the blue lines. And please pay attention here, I'm showing you is the 3D liquid water content. It's not liquid water path, but liquid water content. So if along track, when we have a perfect observed radar reflectivity, and then you can see the retrieve actually is quite well. it's just a sort of a sanity check. You have a radar reflectivity, you have everything, we should do a good job. You may see some pixels maybe not too good, but in general, the retrieved liquid water content is really good. How about a long track? A long track meaning is perpendicular to the, a cross track, meaning perpendicular to the along track. So what you have right now is really just that column, because that column is a long track and that's all you have. The rest is just by the radar reflectivity is assigned by us. So let's take a look at how we retrieved. You can see the left-hand side for the thin clouds, not too bad, but the right-hand side, not too good either, right? So we apparently assigned the wrong radar reflectivity for the across track. And that's what I wanted to highlight here is no matter how hard you match the radius, we are not going to get perfect radar reflectivity. So it is important for us, for the community, really push forward because we need to observe the radar reflectivity even for off-nadirs in order to have a chance to really reconstruct the 3D cloud fields well. That's the first challenge. The second challenge is really about separation species. So if it's precipitating, you have a cloud and drizzle, you have ice and snow aggregates, everything is all together. How to separate the signal in the radar signal or in the reflectance or whatever radiation measurements. So here is, I'm going to show you, and I have to say the remote sensing community really make a lot of development here. I think we did a good job, but still a lot to work on. So here is one example from ARM, our Graciosa radar reflectivity looking straight up. So you can see that's the radar reflectivity. You can see some streams that basically tells you it is precipitating. So ARM has a field campaign and then occasionally go over the site, but that's the only data set we have to evaluate the retrieval. So we can separate the cloud and drizzle. And here I'm show you the cloud droplet number because that's what this audience probably cares most. And so the red dots are from the in situ data. Black dots are in situ data. The red circle is our retrieval. It's quite hard to compare because the in situ measurements typically are 2 kilometers away. But you can see our retrievals are quite sort of falling in the reasonable range compared to in situ measurements. We also have a drizzle droplet number, concentration, size, and water content. And you can see that's the right-hand side that figure that show. For some period, it's good. For some period, you can see, especially at the 10 to 11 UTC, you will see the in situ data has a big drizzle drop, and our retrieval basically are too small. And that's because of some assumption, but I also don't know if the in situ measurements are right or wrong. We have tested some hypotheses and none of them supported that finding. So I actually will be very interested to see pace measurement to see if that's a really common thing to have a large drizzle drop size like that. So this is a warm cloud. How about ice? I really applauded whoever work on the ice microphysics. So here is the in situ measurement. It's not uncommon, right? It's not uncommon. It's common that you have a ice embedded snow. How can you tell the ice number concentration if they are embedded snow? As you can see here is from the UK Picasso campaign. You see the needles, you see the plate, and then you see the snow aggregates. And I picked this campaign because that's at that time is the only campaign I can find to evaluate the cloud retrieval. Why? Because they really dedicated and coordinate so well. The radar is pointing to where the aircraft is going to fly. And that data set is super valuable for us. So let's show you the results. I'm not going to tell you how I retrieved. So the black line there is the in situ number ice number concentration. The red dots are our retrieval. The gray dots are based on some sort of a regression relationship. And you will see that that's what I would like to really point out. You can see if you just using sort of an empirical relationship, it's going to be bias high. And why that's high? Because they didn't really consider that ice is embedded in the snow. So a lot of the reflectivity actually is coming from the snow, not from the ice, not the pristine ice. So it is very important to separate two species in order to know their relative contribution. So I'm quite happy with this, but we still overestimate 98%. And this figure is showing the diameter, because the diameter actually is important. But you see it actually results are very confusing. And I realized that I've spent a lot of the time to understand this figure. It turns out the ice cloud the vertical gradient, the probability actually can be quite large. So where the aircraft is flying is going to be very important when we do the evaluation. I'm not going to talk about this, but this is the field campaign from ARMED a long time ago, the field Finland. What I point out here is I think it has everything at that time. Has a ground-based in situ, has the radar really look at the along wind to allow to see where the ice or secondary ice production occur. And we need that, and we also need aerosol information in order to get the sense how to do the ice microphysics better. And that's what I think is important. Just bear with me. So you wanted some next steps. So here is what I think we need to start thinking about. I think we do need to deploy a dedicated and coordinated is the key word here, big field campaign, can be from many platforms. And we also need to develop the capability to observe the 3D clouds so that we can do the Lagrangian analysis. And the third one is something I'd like to ask you, because I haven't really heard that much, is I don't think we have a defined clear size requirement for key aerosol, cloud, and precipitation observations. And it doesn't mean we can achieve now, but it would be nice to know in order to work toward. And the other thing is for the remote sensing community, I think we should work harder to improve the quantification of retrieval uncertainty. But modelers and data users, please do consider better incorporate our uncertainty. It really breaks up my heart that we work so hard on quantifying, but no one uses it. So.
Thank you, Christine, for a great talk. The next presentation is a contributed talk given by Graham Feingold from NOAA.
Okay, thank you very much. This is going to be a little different. I'm just going to address a very simple aspect of our problem. And this is associated with what we can do with snapshots of atmospheric fields. How can we learn something about processes? And co-authors are listed right here. So the first, the challenge I want to place over here, put in front of you over here is, can we infer process from snapshots? Example here, can we learn the rules of football from infrequent snapshots of the game? And of course, there's an assumption, maybe obvious, but you'll see why I make it explicit, assuming the rules of the game do not change. Why do we care about this? Well, for years and years, we've had polar orbiting satellites giving us snapshots once or twice a day. We have aircraft flybys. Snapshots give us great statistics. They give us statistics of the system state. But what we really would love is temporal evolution, which gives us process understanding. And of course, we do have geostationary satellites, but I'm addressing right here the issue of the polar orbiting satellites. All right, so first example, profiling drop effective radius using cloud top retrievals. This is purely from snapshots. This is something that was introduced years and years ago by Rosenfeld and Lenski. I think it's a really good example. Rather than sample snapshots at different times, why don't we just take a single snapshot and look at clouds across that field at different stages of evolution? And there's a built-in assumption over here that there's negligible variability in meteorology and boundary layer properties across that image. Or in other words, the rules of the game don't change. So what are we really doing here? We're taking each cloud. This is just a schematic. We're taking the drop effective radius at the top of the cloud. Each of those clouds could be at different stages of its life cycle. We build an effective radius profile, the top right over there, from the tops of the individual clouds. And we connect them and we get something of a profile. And you may be skeptical about this. I was, and some years ago, we thought we'd use LES output to see how well this works. So here's some LES output, shallow marine cloud, cumulus clouds, 3 panels. At left, we have high concentrations of input aerosol, 2,000 per milligram, all the way down to 25 at right. This is all the model output just plotted as a profile, and the black solid line over there is the median. So that we'll call the model output truth. And then bottom panel, 3 panels, we have mimicked the Rosenfeld-Lenski method, assuming perfect retrievals. And now you see, and then just lift that median from the median lines from the top 3 panels, place them down below. You can see this method for this particular case looks quite good. There's a little bit of an offset, but altogether it captures that profile quite well. So at this point, I want to bring in the concept of ergodicity, which many of you might know about, maybe know a lot more about than I do. But let's just present it to you and go through a few thoughts. One of the definitions of ergodicity is that if you have a sufficiently large collection of random samples of a process, it could represent the average statistical properties of the entire process. I know that's a lot, and I'll just give some examples in a minute just to present it in a more clear way. It's often thought of as a time-space exchange, and I think you saw that in the Rosenfeld example. Instead of waiting to watch a cloud go through its evolutionary process, you looked at a spatial distribution and then you sampled that into a profile. So here's an example of an ergodic system. Whether one person rolls a die 100 times or 100 people roll a die once, the expected outcome is the same. That's an ergodic process. Whether one person plays Russian roulette 6 times or 6 people play Russian roulette once, the outcome is very different. So that's an example of a non-ergodic process. Let's go back to this effective radius profiling. What does the success in effective radius profiling mean? I think, and I still have some work to do on this, that there's self-similarity in this cloud field that's growing in a relatively homogeneous environmental environment, and that the aspect ratio is essentially telling us something about the net entrainment in that cloud field. And you can see here a plot just from one example showing the aspect ratio in the black dots, aspect ratio defined as this parameter beta, and Z is proportional to area to the power beta, and entrainment on the right axis in those colored points. And you can see good correlation over there. This is just an example. I just want to point out that really the issue here is not only do we think we can profile the drop effective radius, but we might be able to get at entrainment in clouds through the aspect ratio of these clouds. Still work in progress. Okay, example number 2, compositing of a stratocumulus cell from a snapshot. So here we have a different example. We've got a cloud field at bottom left over there, closed cell stratocumulus. I've just put some boxes there from we could sample from different cells across that field. And the hypothesis is that the processes in a canonical stratocumulus cell can be understood by compositing samples of many different stratocumulus cloud cells. So again, we're looking at spatial sampling, being able to inform us on process understanding. And again, the assumption is that we have negligible variability across that field in terms of meteorology. So the rules of the game don't change. Here is the method of Bretherton and Blossy, and in this particular case, it's Shaoli Xu and Bretherton's paper from 2019, where they have taken the total water path across an LES scene. This is purely an LES example. And essentially what you do is you build the percentiles across that scene, and you take those percentiles, sort them from 0, total water path, all the way out to 100, composite them across the scene, and you build this kind of plot over here, altitude versus percentiles of TWP. This is a zoom in close to the inversion. You can see immediately from the flow field in the LES that you have convergence in the boundary layer, you have divergence aloft, and that solid thick line is the inversion. So you're already starting to see something appear from these samples across a field that are just disparate parts of that cloud field. And this was the picture that they came up with, which fits our understanding quite well. You can see the structure of the closed stratocumulus being explained by the composite of these different cells across the field. The key point over here was that this radiative cooling, this differential radiative cooling from the center of the cell towards the edge of the cell is helping sustain this mesoscale circulation that keeps the cell, this closed cell structure. Now, I can't go into the details over here. It's just another example. And the final example I want to give is just thinking about a cold air outbreak. This is work by Jian Hao in my group. This is a GOES snapshot. This is not, we're not using GOES because we're interested in the temporal evolution. We're just taking a given GOES snapshot of a cold air outbreak. And at bottom left, you can see a whole bunch of trajectories going through that cold air outbreak. We have from the GOES snapshot the liquid water path, the drop number, the cloud albedo. We also have ERA 5 for the meteorology. And the question here is, can one infer processes driving this cloud field evolution from running a trajectory through that snapshot? And what I'm showing here is the liquid water path, drop number, geophysical variable space. So let's think about processes in that space. So look to the right panel over there. I don't think I can point with this, but look to the right. If we were if we were looking for a signal of activation, we would see number 1, that would be an increase in drop number, an increase in liquid water path. Condensation would obviously be an increase in liquid water path, no change in drop number. Coalescence would start pulling us to lower drop number, but at constant liquid water path, and so on and so forth. You can see how we might be able to see the fingerprints of different processes. And in the middle down there, you can see an example of one of these cold air outbreaks. And in a bit, I'll contrast 2 different examples. But our claim over here is that the shape of these trajectories encodes process. There are both meteorological drivers over here, and there are microphysical processes. Just to give an example of the meteorological drivers, as you come offshore, move over the ocean, the boundary layer is going to deepen, and so the liquid water path will tend to increase. So you've got both that process plus the microphysical processes. But let's contrast 2 cases over here before we wrap up. At the top, a precip-driven breakup, the example I just showed you. You see this evolution through the activation, condensation, collision coalescence, and then crossing that 15 micron line where we think precip is more likely, we see that break up into the open cells. The case at the bottom is an entrainment-driven breakup, has a very different fingerprint. You see the increase in the large-scale meteorology is again driving that increase in boundary layer depth. We have activation going on. We have some condensation. We never get to that 15 micron precip line, and you see how you essentially entrainment starts to pull that line down. I wish I could point, because then I could show you exactly what I'm referring to, but trust me that I think we can discern the differences between precip-driven breakup and entrainment-driven breakup. So I'll just wrap up then. I gave you an example here of, well, I've tried to show you some examples of how I think we can infer process from snapshots. The first one was the profiling of effective radius. I think that this implies self-similarity across the cloud field, and that not only can we potentially sample effective radius profiles from the tops of these clouds, but we may also be able to learn something about entrainment. Stratocumulus compositing to infer process was the next example. One randomly samples a field, sorts by the total water path, and we think this provides insight into process, and this is really Bretherton and Blossey's idea. Then the final example is this time-space interchangeability in a cold air outbreak. The dominant meteorological and microphysical processes can be identified. We could easily distinguish between the precip-driven breakup and the entrainment-driven breakup. Key over here is that the large-scale system evolution needs to be slower than the processes being explored. And then just one final slide with some comments. I brought in this concept of ergodicity, which I would like people to think about. Exploiting it to the extent that it exists is a powerful way to utilize large samples of snapshots to infer process. Strict definitions of ergodicity may not be necessary for snapshots to be useful for understanding processes. And then finally, there are some practical aspects that may get in the way. For example, effective radius profiling, one of the examples I showed, is quite difficult in broken clouds, particularly with traditional Nakajima King's type retrievals. So these are some of the issues that could get in the way of, the imperfect retrievals might get in the way of really leveraging ergodicity. I'll stop there.
Thank you, Graham, for the nice talk. Let's shift the gear towards the aerosol retrievals. The next presenter is Meng Gao from NASA Goddard. He's attending online.
All right, so thank NASA for the introduction. So I'm working with NASA Goddard and with PACE satellite team. So I really enjoyed this workshop. And so I want to provide some of our perspective from satellite remote sensing point of view. And so Nadine sent us a really nice summary on this, on the microphysics. So basically, so my talk will fit in the second step. Basically, we'll try to derive some aerosol microphysics, like their size, refract index, and based on this kind of optical remote sensing, and that will be like in a global kind of scale. So I don't know how many of you have heard about the PACE mission. So we have this satellite launched this year on February 8th. So it's about 8 months ago. Okay, basically, so we have this satellite launch, and it's been running for 8 months. So we have collected a lot of data. So we are trying to derive useful product from that. And I want first to start with some really brief introduction about our mission. So this is basically the last moment we can see the satellite before it's drifting away in the space. And we have 3 instruments. So if you look closely, there are 3 instruments here. And so the major instrument is the biggest one, that's called the OCI. It's a hyperspectral instrument which covers from UV to near infrared band. Also have several shorter infrared band. So it's provides really great spatial coverage. Basically, have a 1 to 2 day global coverage, and it also can tilt. So that's it's designed to avoid angling, but probably can also have aerosol retrievals. There are also two multi-angle polarimeters, and they are HARP2. The HARP2 instrument is built at UMBC. It measures 4 bands at many angles. So some bands have 10 angles, there's one band have 60 angles. So it provides a lot of multi-angle capability. It also share a similar swath as OCI. For SPEX1 is built at Netherlands, the iStrong team, and so it's also a hyper spectral instrument. It's measure 5 angles, but at really narrow swath, about 100 kilometers. So basically, these 3 instruments are really complementary to each other. It provides a lot of capability for us to study aerosol cloud and many other things. So we have released the version 1 data, and so that including all the level 1 measurement from all the 3 instruments. And that is released at April 11. And after that, we have been also improved calibration. So that is the version 2 data, which is also released in this summer. We also have some sense data, level 2 data available. But mostly it's covered the ocean studies. And we're also planning for more atmospheric related product, which will be released soon. And just to give you a overview, so what it look like from PACE, and this is from NASA worldview. Basically, you have this kind of global coverage. This measurement is taken by OCI. For other instruments, you have more spectral and also have multiple angles, which probably can help study 3D cloud, for example, and also with polarizations that provide a lot of capability to really get into the details of aerosol studies. And so the data product for aerosols derived from the polarimeters actually include quite a long list. So we have a PACE data product table, which is available in PACE website. So we provide color-coded data products, which is we indicate when they will be available. So basically, they are including aerosol optical properties, like their Feingold, Cosmode, aerosol optic depth, single signal albedo. There will be also aerosol microphysics that will be related to aerosol size, their shape, complex reflect index, derived from their optical measurement. And then we also aerosol layer height, and also we have these surface properties because there's a really rich information from this polarimetric measurement. So the surface properties can be retrieved simultaneously with the aerosol properties, and we will release them all together. And there's 4 algorithms have been tested to derive this aerosol properties. So they kind of optimize the information different ways, but also have different assumptions. So I won't really talk too much about each of them individually, but I will using the last one. That is the one we developed in-house, and to demonstrate what is the capability of those retrieval algorithms, and also what kind of product we will have. And also I want to explain a little more. So why we are interested in polarimetric measurement. So what is the promise from that? So basically on the figure on the left, so that is a retrieval. If we only have a reflectance measurement from, for example, HARP2 measurement, there are 4 spectral bands. And if we only have this reflectance measurement, and in this plot, we have the x-axis is aerosol refract index, y is aerosol size. Basically, it's really hard to separate these 2 properties. They will form this kind of valley. So sometimes there's not unique solutions. But when we consider polarizations, as shown on the right, so there is a really good opportunity, or really you will have a higher accuracy to really pin down their reflect index and their size together. So this is why we're interested in this kind of polarimetric measurement. But that doesn't mean we can retrieve everything. So we do make a lot of assumptions in our retrievals. So one of the assumptions is that we have to assume the aerosol size, they only varies within a certain range. So for the aerosol size, which is too big, because of our spectral measurement have a limitation, so we cannot really retrieve aerosol with a large size in really good accuracy. And we also try to retrieve aerosol types directly, but we have to make assumptions. There's a size and refractive index, they kind of relate in certain ways. And we also have been testing the retrieval aerosol shapes. So basically, we have tried aerosol retrievals with the spherical shape and the spheroid shape. They are really popular in the remote sensing community. And most recently, we have also been testing the irregular hexahedron database, which is produced by Masa's team. So that is also something we are trying to do. But in order to compare those aerosol models, it's really challenging. But that's mostly related to the huge computational challenge to really retrieve those data in a really large scale, and because there's really high accuracy requirement, and also there's there's so many measurements there, and it's really hard to fit them in a really efficient way. And also, I think Kristen mentioned about the uncertainty analysis. We also try to really quantify the uncertainty. That's also a lot of challenges. So we spent some effort to really try to improve the speed, to speed up also quantify uncertainties. So I want to using this the fast Maple algorithm as an example. So basically, in order to improve the speed, so we have to have really efficient form model. That is the transfer form model. So we spent some effort to develop a kind of neural network emulator, which can represent the form model retransfer simulation really efficient. So we can retrieve this retrieve the aerosol properties and also surface properties together. So they're really high dimension of retrieval space. And based on this, we can also start study uncertainties. So I will show you really briefly what kind of uncertainty study we have done. So I won't really get into details. On the right side, basically the uncertainties we try to address. So we look at every product, every property we retrieved, and to see how their retrieval uncertainties will varies. In this case, I'm talking about how the retrieval uncertainties varies with the number of input angles. Basically, how many valid measurement is available there. And if we just focus on the figure on the left, basically, if we have like 20 angles, the uncertainty can reduce really fast. And then later on, when we have more and more measurement, it still can reduce, but it's getting slow. And this is also the concept we developed a data screening approach. So basically, we look at our retrievals, we compare the form model with measurement, and if the measurement cannot be fitted by our form model, that's most likely there's something happened. For example, there's some cloud blocked some angles. We will remove them, and then we will reduce the total number of angles, but we can still get some valid retrievals just with a higher uncertainty. And there's another uncertainty study we have been done. So in this case, we look at how the retrieval uncertainty varies with aerosol optic depths. So basically how much aerosol are there. So we will have higher uncertainty with aerosol optic depths, but for microphysics, we will have a higher accuracy when there are more aerosols. So that's kind of intuitive understanding about that. And with that, we also try to understand how we can really understand from a more theoretical point of view. So we propagate our measurement uncertainty using the Jacobians to the final retrieval uncertainties. That's basically the red line showing here, compared to our retrieval uncertainty, which is derived from our retrievals compared with the truth. So we have actually can match them pretty well. That means we kind of can retrieve most of the information from this study. And then we can, using this approach, we can provide pixel-wise retrieval uncertainties and just through error propagation. And in this work, so we also try to look more closely, more details on the measurement uncertainty by considering whether there's a correlation between different angles. Because for the measurement we are treating here, this is for the HARP2, they have 90 angles. So there's maybe some correlations between different angles. So we spend some effort trying to understand that. So basically what we found is when there are correlations, we do see the real retrievals uncertainty actually increase, but our theoretical prediction through error propagation actually reduce. That's because we have a stronger constraint on the uncertainty model. So there should be more information available, but we still haven't really understand why there's they deviate from each other. And this is extremely difficult to understand because we don't really have a good understanding on like how strong the correlation available or existing here on the real measurement. So if you have any like suggestions of ideas, please let me know so we can probably understand what is happening and further help the retrievals. And so last year, so before we have the real pace data, so we simulated, we try to simulate the more realistic synthetic data. In this case, we use Mera2 aerosol model as input. So we conduct like global scale simulations, and here are just the examples for the retrieved aerosol object depths and also their pixel-wise uncertainties. So we can do similar summary and similar to what I showed you before. And so in this case, and we can understand the retrieval uncertainties in a more realistic aerosol input. I think I gave some message. If there anything you cannot see, please just let me know. Otherwise, I think I will continue. I don't really have any videos. So basically, in this study, we have a more realistic aerosol input, and the uncertainty will be more representative to the real scenarios. And what we found is for Feingold retrievals, actually the retrieval uncertainties between the real retrieval and the error propagation results, they can match each other very well. But for Cosmos, it's getting really hard. And we can still see they have a larger difference. So that means probably for Cosmos retrievals, the solution is not unique. There could be like a local minimum. So here I will show you some real retrieval results. And this is based on HARP2. And for HARP2, we have all the 11 data already released. But for the calibration and the reflectance, the radiance part is already quite good, and the polarization part is undergoing final tuning. But we can already retrieve good aerosol properties. And in this case, this is indeed a video. I don't know how well you can see it, but basically it's this is retrievals for from April and May for daily image, and so you can see the propagation of these aerosols. I think someone can see it, so that's great news. So, and basically you can see the propagation of aerosol from the Sahara Desert, and also you can see there's a larger aerosol loading near this Asia area, probably some polluted aerosols.
You have about 1 minute.
All right. Okay.
Thanks.
So just some final examples. We'll also look most closely to see like how they look like from AOD and also their size. And so most recently, so last month we have a whole month PacePax field campaign. They have a lot of in situ measurement, so we can also compare with the LiDAR. Basically, what I'm showing here is a LiDAR measurement compared with our retrievals. And so we have many different scenarios with different aerosol loading. Also, sometimes with the completed aerosol cloud interaction probably. So this is very interesting to look at. And so we have also looked at spectrum data, but I won't really talk about too much details here. But the data is really promising. We can also retrieve ocean properties together, but they have a narrow swath, so you can see the stripes kind of thing here. So okay, I will just wrap up here. So so what I want to say is there is a lot of data available. So we have been doing a lot of work, try to improve the data quality. But we're also very interested to your feedback, whether we can make our product more useful to the climate community. And we have a application workshop which will happen in the weekend before AGU. So if you're interested, please consider to register. We also have a lot of online materials. So I will stop here. Thank you for your attention.
We're running a few minutes behind, so we're going to press on. Our next talk is by Elise on molecular simulations to provide evidence in support of ice nucleation upon collision or breakup of supercooled cloud droplets.
Thanks. So here on my title slide, I'm posing this question: do supercooled cloud droplets freeze during collision coalescence with each other? And I won't be able to provide a definitive answer by the end of this talk, but I will be showing some recent progress using molecular simulations, which show that water under tension increases its freezing temperature, and I'll explain how that's related to this droplet coalescence case. And this is work I did with my PhD advisors, Raymond Shaw and Will Cantrell, and a few collaborators. So brief history, in the 60s through the 80s, there was a handful of papers that were published speculating that perhaps supercooled cloud droplets freeze when they collide with each other, or if a large supercooled rain droplet breaks apart, maybe that triggers its freezing. And there hasn't been much investigation into this possibility beyond this handful of papers, but these authors were proposing that this could be a cloud glaciation mechanism. And they were motivated by the fact that violent motion of supercooled water will prompt the water to freeze. And the more violent the motion, the higher the probability of freezing. Excuse me. So this is termed mechanically induced ice nucleation. And the physical explanation for why this might happen is very unclear at this point and has been for a long time. And a key reason why behind this unclarity is because our ice nucleation rate equations are predominantly temperature dependent. So here I have J, ice nucleation rate, and with A and C as constants, we have temperature dependence in the denominator. And but the main driver is this chemical potential difference, delta nu, and the amount of supercooling, which is that T melt minus T term, is the main driver for increased ice nucleation rates. But in these mechanically induced cases, temperature is constant, but clearly the ice nucleation rate is increasing, so that's somehow not being accounted for in our equations. But perhaps if we add a pressure dependency to our ice nucleation rate equations, this could help explain these constant temperature phenomena. And the temperature dependence can be added into the chemical potential difference, delta nu, shown by this added delta P, delta VLS term, where delta VLS is the volume difference between the liquid and the solid. Since that's going to be negative for water, that means we need a negative pressure perturbation, a negative delta P value, in order to increase our nucleation rate J. And to achieve a negative pressure perturbation in water, that means we need to place the water under tension. And this is sort of a schematic showing water in a vessel with sort of a piston pulling up on it. And that shows how you can place water under tension, and that water will have a negative pressure value inside that volume of water. And another important concept that was highlighted also earlier is also during mechanically induced ice nucleation events, experiments highlight the role of the air-water interface as being important. So these are two experiments done at Michigan Tech, and you have a supercooled droplet resting on a uniform substrate, and the temperature is constant, and the experiments find that enhanced ice nucleation on this substrate is only observed when the surface of the droplet is stretched from its equilibrium shape, inducing curvature at the air-water interface, which you can see a lot of curves and ripples at the edge of the droplet. So how does this air-water interface curvature relate to the pressure dependency? Well, the hypothesis is based on the fact that curvature of the air-water interface creates Laplace pressure. And a lot of us are familiar with positive Laplace pressure in small droplets, but negative Laplace pressure is produced by concave water surfaces. And this schematic shows a water capillary bridge, so water droplet sandwiched between two, in this case, hydrophilic substrates, and the air-water interface is forced into this concave shape, and surface tension is providing a constant outward force on the water and producing negative pressure in the capillary bridge. And no mechanical motion is required to produce negative Laplace pressure. It's just created by the curved air-water interface and the surface tension. So now the droplet coalescence comes into the picture, because during droplet coalescence, The air-water interface experiences high degrees of curvature, and this simulation of droplet coalescence showing the pressure field shows regions of blue, which is negative pressure, anywhere where the droplet surface has this concave curvature. So this has been a lot of speculation over these decades, and so we wanted to use molecular dynamics simulations to demonstrate a direct quantitative link between the presence of negative pressure in water and increased ice nucleation rates. So this is an example of a simulation box where the cyan spheres represent water molecules and the brown spheres are a hydrophilic substrate on which the ice can nucleate. And to find the ice nucleation rate, we do a process similar to experimental methods of calculating ice nucleation rates. So we set up a array or an ensemble of identical boxes of water, and we set them to all to the same pressure of interest. And then we cool them all at a constant cooling rate, which the number counting down is showing the temperature going down for all these boxes. And then we record the freezing temperature distribution across all of these simulation cells. And so with the freezing temperature distribution, we can get the ice nucleation rate as a function of temperature. And we repeat this for different negative pressures of interest, creating a new ensemble of identical boxes at a negative pressure of interest and running the cooling ramps to find the new freezing temperatures. So the results of the simulations show that negative pressure can increase the ice nucleation rate without changing the temperature. So this figure is showing pressure on the x-axis and temperature on the y-axis, and the colored contour lines are lines of constant ice nucleation rate from our simulations. So as an example, if we were to start with an ice nucleation rate of 10 to the 21, and we want to increase our ice nucleation rate by 3 orders of magnitude, we could lower the temperature, and this is what we're typically accustomed to. But we could also remain at the same temperature and lower the pressure and still reach the same 3 orders of magnitude increase in your ice nucleation rate. So if we make the assumption that these contour constant nucleation rate lines are linear throughout this pressure range shown here, then we can solve for the slope of the curves, or this relationship delta T over delta P, using the pressure-dependent ice nucleation rate equation shown earlier. And the slope ends up depending on these 3 physical variables, which for water comes out to having a slope of 0.007 Kelvin per atmosphere of pressure change. Another thing we did was we wanted to demonstrate with the simulations that negative Laplace pressure can produce the expected increase in freezing temperature. So without setting the simulation to a negative pressure, the negative pressure is coming from the curved air-water interface in this capillary bridge setup. So H is the height of the capillary bridge. This delta P is the expected Laplace pressure in this setup, where sigma is the surface tension, theta is the contact angle of the water with the substrate, and then by varying H, the height of the capillary bridge, we can get different amounts of Laplace pressure in the water. And using the slope equation from the previous slide, we can estimate the increase in freezing temperature due to this negative pressure in the capillary bridge. And so we saw the results that we expected, which is that negative Laplace pressure leads to increased freezing temperature in the capillary bridges. And I'll just point out the scales that we're looking at. So our capillary bridges are nanometer length scale curvature, radius of curvature. The pressures are hundreds of negative atmospheres, and the increases in freezing temperature are on the order of a couple Kelvin. So Yeah, so now as a start, to try to understand how these negative pressure perturbations could have impacts for ice nucleating in the atmosphere, we can start by thinking of like a pressure enhancement factor to quantify how a certain amount of negative pressure will impact active IMP concentrations. So we typically think about the number of active IMP as a function of temperature. So that's that N sub I term. And we can define a delta T sub P, which is going to be the increase in the activation temperature of the INP due to a negative pressure perturbation, delta P. And using that, we can then define a delta Ni, which is the increase in the number of active ice nucleating particles due to their increased activation temperature. And that's dependent on the slope of the IMP function as a function of temperature. So then we can define this enhancement factor, which is comparing the number of newly activated IMP due to the pressure perturbation normalized by the original amount of active IMP at that temperature. And using that expression, an enhancement value equal to 1 would mean that the IMP concentration has been doubled. And so now I'm showing an example of like IMP curve, number of active IMP as a function of temperature. And 3 commonly used parameterizations are shown in those dashed lines. And the curved line shows a more complicated curve from filter collected IMP in the field. And if we use the Fletcher 1962 example and work through the enhancement equation, we would get an enhancement of 1 from negative pressures of minus 200 atmospheres. So that would mean, for the Fletcher case, a doubling of IMP concentrations across all temperatures. And I just wanted to point out that because of the dependence on the slope of this IMP curve, in the warm temperature regions where the slope is really steep, you would expect higher enhancement values. So it would be more sensitive to this pressure effect in those warm temperature regions. If we were to assume that that 200 atmosphere of pressure came from Laplace pressure, from surface curvature, that would require surface curvature on the order of 10 nanometers. But that brings me to my final slide, which is just to say that sources of negative pressure in cloud droplets is something that has yet to be investigated. The results from our ice nucleation simulations show that any source of negative pressure in water will lead to higher ice nucleation rates. But again, it's uncertain what sources of negative pressure are active in the atmosphere. And some processes that have been speculated on are droplet coalescence, contact nucleation. With this picture I put on the slide, kind of shows a macroscopic example of why a particle at the surface of the droplet would lead to surface curvature and could have this type of thing going on. And also the ice nucleating particles at the air-water interface that Nadine presented earlier is also really interesting to me because it provides nanometer length scales, which, as I showed, those are the length scales required to produce hundreds of atmospheres of negative pressure, which are associated with high levels of active IMP enhancement. And since I just have a quick minute left, I think I'll just show this. Oh, okay, that's okay. Hundreds of atmospheres of negative pressure happen in nature, so it's not like an unheard of thing. Thank you.
Three, perfect. Okay, so similar kind of structure as before. If you have questions, please come up to the microphone. Not all of you know each other. I certainly don't know many of you. So please state your name and your affiliation, and then ask your question. And if anyone in the audience has something they would like to chime in about that question, maybe a comment, an answer, or a follow-up question, just raise your hand and we can pass one of probably this microphone to you, so you don't have to wait in long lines. Is everyone up here? Cool. Okay.
I had a question for Graham. I really liked your way of thinking. Yeah, I really liked your way of thinking about the evolution and how we can learn from that. But in a cold air outbreak, I mean, you have a cloud at the beginning of the cold air outbreak. It's a little cell, and it forms and then it dissipates, and then it forms and then it redissipates. And by the end, you have a cloud cell forming and dissipating that there's no history linked back to the one that was at the start of your cold air outbreak. So how does that affect your view of evolution when really it's just dissipation and reformation all the way along that trajectory?
Well, I mean, that's true of looking at any cloud. The cloud, you know, the drops have a lifetime that might be 15 minutes or a half an hour, and that cloud gets constantly regenerated. So meteorology is constantly regenerating a cloud field. And the cold air outbreak is an example of a cloud field that is evolving as it moves across a warmer ocean surface. And you're seeing a manifestation of that system, the system evolving under constantly changing conditions.
Yeah, but for something like precipitation, which will, you know, it's not the same cloud which is precipitating, losing water and showing up at the end of your colder outbreak. It precipitated, it dissipated entirely and then reformed and started precipitating anew. So I don't see
That's
how
right.
precipitation is a connecting variable for in that case.
Well, the precip is driving the system in some direction, and you're seeing a manifestation of that. This is just a sort of global view of the system, and you can see fingerprints of that in those traces, but there are, you know, you're just seeing indicators. It's not a unique, you know, when you see the system moving in a direction, it's not unique. You're seeing different processes pulling it in different directions, but it's not a, you know, that's a combination of precip, removing liquid, it's, you know, condensation growth if that's occurring. All those processes, those warming processes are driving the system as it moves along.
Very nice talk, all talks. I have a question for Chrissy Chiu. You mentioned like the aerosol above the cloud can get like enhanced direct radiative effects, especially for flower and fish clouds. Or so generally when we calculate the cloud radiative effect (CRE), we use all clear sky minus all sky minus clear sky. But seems like if there is an enhancement of aerosol direct effects caused by clouds, the way we calculate that actually not only includes CRE, but also includes that. Is that?
Yeah, sorry. It's not caused by clouds. It's a big, okay. No, I think maybe I didn't make it clear. Is it the cloud radiative effect, 3D cloud radiative effect enhance the reflectance? And that reflectance needs to you need to deduct the 3D cloud radiative effect in that reflectance in order to do the retrieval. Once you do the retrieval, so that is all about aerosol direct effect, so with and without aerosol.
The room.
So it has nothing to do with the cloud radiative effect. Yeah, it's not, I don't think he is talking about CRE.
I mean, but you mentioned the aerosol have like a high score speed.
Yeah.
Yeah. I mean that in that case, I guess do you have any comments like how much uncertainty will be introduced by the method we use to calculate CRE?
Don't know. Have to think about that. That's a good question.
Thank you.
Hi, this is a question for Graham. This is Marcus Spangler-Walke from Columbia. So some of your assumptions are sort of this, the rules of the game don't change. Like how good is that assumption? Can it be quantified so that you can kind of have some sense of the information content that you're actually retrieving out? How strongly to weight this if I'm comparing it against a model, for example?
Well, I think that's fairly easy. I mean, if you've got a snapshot, one of the things that's pretty obvious is you'll see some boundaries in that cloud field that make it very clear that you moved from a certain cloud type to a different cloud type. And it's very likely that you've got different driving conditions driving that. And so, yeah, you want to automate that if you're going through lots of observations to figure out the extent to which you have constant meteorological conditions. We haven't looked at, and this would be another level of effort, the extent to which that meteorological field needs to be constant. And there's the other aspect, which is those clouds are forming in that environment. They're driven by that environment, but then they're modifying that environment. And that becomes quite interesting. So if you had one of those effective radius profiling systems set up and you started to get precip, you might find that that was stabilizing the system to the extent that you may not be able to do that, use that method anymore. It's for me, it's just, you know, at this point, just an idea rather than a practical effort to apply it broadly.
Hi, Andrew Gettleman from PNNL. So a lot of great talks, a lot of things to think about with respect to observations. And one of the things that we often struggle with, I think, when comparing observations to models, especially when we're working with models and we're thinking about climate, where we're having to parameterize things at a large scale, which is the wrong scale for microphysics, is how do we deal with inhomogeneity within the observations? And it starts with what Elise was talking about at the drop scale and the inhomogeneity in the environment all the way on up. And more specifically, I'll throw this question out there, and I'll buy anybody a bottle of wine or a case of beer who can answer this question in the room. How mixed is the mixed phase?
Was there a question there, Andrew? Oh, no, I'm not going for that. But you're talking, yeah, could you just rephrase? There's a question that first.
So and it gets back to sort of what you were talking about with some of these scenes and stuff, and taking pictures of the different parts, even of a stratocumulus cloud in the case that you were looking at, and trying to understand, are these each uniform, or is there variability within them that we have to worry about, and how are we applying that to different scales of what we're trying to represent in a model? And you could also talk about it in the vertical, like from the other example that you were given. So there's a bunch of different things going on there.
Yeah, I mean, I don't have anything coherent or very intelligent to say. Let me think about that. Maybe I'll, yeah. Maybe,
yeah.
And Nadine
also.
after.
Hold on, Nadine.
I was as I've been thinking about the problem that I was working on, I was really interested in a paper, I think it was published either this year or last year by Louise Ickes, and developing a new ice nucleating particle IMP concentration parameterization using like sort of a probability distribution at each temperature rather than a fixed number concentration at each temperature. And they did some sensitivity tests using that with an LES and found that like the standard deviation of your probability distribution, like how wide your range is of IMP concentration that you can pick from at that temperature, makes a pretty big difference in how much ice is formed in these clouds and then the subsequent processes. So I think it is really interesting, common thing I'm seeing that small perturbations outside of your like average value can end up leaving a lasting impact like on the cloud system.
Nadine?
Yeah, I think that Nicole this morning, explained it really well, that the aerosol complexity is really large, and it's going to depend on your sources, on your aging process. And as a chemist, I can tell you that every single aerosol is a tiny little reaction vessel with lots of different chemical reactions happening simultaneously, changing the microphysical and chemical composition of these aerosols. So the complexity of the aerosol then impacts the complexity of the ice nucleating particles. I will say, though, that at the end of the day, I often think of ice nucleation something as maybe I'm going to get thrown tomatoes for saying this, but as a binary process, because your droplet is either frozen or not frozen, unless you have a high-speed camera and you can watch the process. But and so what you're really looking at for ice nucleation is the most active ice nuclei. And so in the mixture of all those aerosols with all those components, you're going to have lots of different substances that can nucleate ice at different temperatures, at different rates. But really what we want to capture is what are those really, really effective ones, because then they will dictate that ice nucleation. They will dictate that temperature, and that's what we want to know.
I'm Kenta Suzuki from University of Tokyo, and my question goes to Graham, because I'm also following the approach similar to what you talked about based on the snapshot statistics. So I'm always wondering about how such kind of snapshot-based statistics can tell us about the causality between the two variables or multiple variables that's used for constructing the statistics. So I'm talking about the causality of the some processes between, for example, one variable with another variable. And maybe the regime classification that you talked about might be hinting at such kind of understanding of the causality, but that's not very clear to me. So can you make any comment on how to, think about the causality based on such snapshot-based statistics?
Think about is the liquid water path drop number plot, which many have looked at. I mean, if you took a large ensemble of large eddy simulation output, and in my group, people have done that, including the work that Francisca did and Fabian and others, Yao Sheng, you can take that model output from hundreds of LES, and you can do an analysis, a budget analysis of the model output and get at the processes. You can get at the evaporation, the precipitation, the radiation, and all those processes, and you may use mixed layer theory for that or some variation on that theme. But you can really clearly, in that liquid water path drop number space, identify the processes exactly where you expect to find them. And so to me, that is a connection to process, but that of course is a large ensemble of LES in very well-defined conditions. Now let's take satellite, large, MODIS output like Ed Grispiet has done, collate all that data, you get this inverted V. How well can we quantify the slopes of those lines? And I think this is where things get interesting. First of all, I think that the quantification is something we have to be very careful about. For example, the rules of the game, to use my terminology, are changing when you take 60 north to 60 south, liquid clouds, many different meteorological conditions. Those slopes are some sort of a mean, but I think you have to be careful about quantifying them and saying this speaks to some, the negativity of that slope, which has obvious implications for albedo susceptibility and whether you can brighten a cloud or not. I think we have to be really careful of that, about that. Yao Sheng has a lot to say about that. He's here, as does Fabian. They've got different posters looking at different aspects of this. I'm very happy to have a conversation about that. Time scales of the processes, I think, are also something that we need to think about, and there's more work coming out of our group and others on that aspect. That's just one. The liquid water path drop number is one we've spent a fair amount thinking about. You, of course, have done the radar reflectivity optical depth, and I think you could probably speak more to that.
Okay, so but anyway, the point is to combine with some models to look at the kind of sensitivity to different processes to understand observation-based statistics, right?
I think so, if I understood you correctly, but
Yeah. So you mentioned that using the, for example, LES model to do some sensitivity experiments to the processes to understand the observation-based statistics for the liquid oral bath number concentration.
Yeah, well, I mean, that's obviously something we want to bring together. You know, you've got geophysical variables that you can measure from space or from the surface, and you've got these models that can reproduce those kinds of geophysical variables. And I think it's, you know, we've got to bring in as many of these geophysical variables as we can to constrain the models, or if not to constrain them, at least to give them some idea of how well they are working. And this, I think, goes to the work that's being done at GIS and other places, you know, really trying to understand, you know, these, you know, two variables there's still a lot of wiggle room. 3, 4, 5, 6, you start to constrain things. And well, there's a whole other aspect to this that I won't go into right now.
Okay, yeah, thank you very much.
Probably do 2 more questions, not to get the hopes up on everyone in line. It's going to be you, it's going to be you.
Okay, thank you. I'm Medical. This is Tony from Barahona from NASA Goddard Space Flight Center. I have a comment and a question. A comment is related to something that Nadine said about trying to find the best or the most active IMP in a population. I mean, if you are on the other side of things that ascribes to the stochastic nature of ice nucleation, actually the whole distribution is important. The most active ice nucleated particles get depleted early during the cloud evolution, and then you're left with the less active ones. But those ones are gonna start a lot of processes that are important for the cloud evolution. So I think it's important to think about ice nucleation in aerosol particle. I think that each aerosol particle has an ice nucleation probability. Not that there is an important magical particle that will create ice. So that's just my point of view. And I have a question about this aggregation of proteins at the interface. I was just wondering if this is more like a dynamic Brownian-like process, or it's driven by thermodynamics. And if it's driven by thermodynamics, I think it is amenable for parameterization, as Elise mentioned, because we can then ascribe some kind of Laplace pressure or decreasing pressure to that. If it is all dynamic, it's kind of more hopeless. So the question is, do you have any idea if it is more dynamic or more thermodynamic?
So thanks for your question and your comment. And let me respond to your comment. I actually very much agree with you that the whole population matters. I think I was trying to, deconvolute the complexity in the question of how important is the mixing state and how deep do we need to go. Because I agree with you that the least active are the highest in number. So I think that how we look at these ice nucleating particle really matters and will dictate what is the most important for that process. I think the problem with some of these drop freezing techniques that we have is that binary issue, that we need to then use Poisson statistics. And there's this nice hub method that was published in ACP by Valerio Molinaro and Conrad Meister to kind of try and deconvolute the subpopulations of INPs that are there. And I think that's important, so I agree with you. As to what is governing the movement and the diffusion, I should say, of the proteins to that interface, I think that's still something that we don't know, and it's because it's hard to probe supercooled conditions. That metastable state is just really tricky to work with. So one thing we're interested in doing now is seeing how reversible the system is. So can we make nanoparticles? Where are they going in the droplet? And then can we poison the nanoparticles, so dissolve the material and see how then they behave? So is the diffusion on a molecule basis or on a particle basis is the question we're asking now. So I don't know that I have an answer, but I'm glad you're interested in that question.
Okay, this is Gwenor Pokrivka from Princeton University. I have sort of a general discussion type question that sort of ties in with the previous session, and also something that Nadine pointed out, where it's like we have all these different studies and methods going on, sort of like spreading resources really thin. But there does seem to be like this hesitancy for funding agencies to allow people to sort of focus in on a particular process or problem. And there is that question still of like, okay, which is more important? Minimizing uncertainty on something that we've already measured or observed, or getting more measurements for things that are unknown. So that's something that was brought up earlier, but I think my sort of follow up to that is if you want to go that approach of decreasing uncertainty on something that we already quote unquote know, how do you convince funding agencies to basically let you redo something that's already been done, but maybe more better?
Excellent questions. I don't know that I have the answer.
I'm willing to take a stab at that unless somebody else would, because I have had plenty of airtime. My view of this is that we love complexity. We've been trained to explore complexity, and most of us come from programs where that's been those are the roots of our graduate research. With time, I think my career has been more about trying to simplify and sort of take more of the top-down view of things rather than the bottom-up. I think we're in a bit of an imbalance, frankly. I think we have a lot of bottom-up, and I think it is quite understandable why we do, and we gravitate to that naturally, but the top-down part of this, the more system-wide view of things, has been neglected. And I don't think it's any less interesting. One could say, well, climate models tend to be more of a top-down, but that isn't really necessarily the case. I don't have necessarily a path forward, but just having more and more people thinking broadly about how do we simplify this rather than how do we complicate. I'll give you one very simple example. We did some work years ago where, in spite of all the complexity in CCN and aerosol cloud interactions, we came up with this notion that cloud systems actually don't budge a whole lot when you perturb them really strongly. And there's an example of trying to simplify things. Does it mean that cloud systems never budge when you perturb them? No, but understanding when they budge and when they don't, and the bifurcation points and that kind of thing is a very different way of thinking about it than saying we need to understand CCN, all the composition issues, et cetera, and you're going to miss some percentage of complexity that might matter at times, but we have to think more broadly, I think.
So actually, like a quick follow-up on that, you were talking about doing a lot of, needing to do more top-down. I would argue that there's also a lack of like the very bottom level with like really fundamental measurements. I'm kind of biased here coming as a laboratory scientist, where there seems to be not enough time provided for laboratory measurements to get enough data for it to be statistically meaningful. So that's how we end up with all these like very specialized complex cases. If we can like have more data from that, then maybe we could have a more broad parameterization available.
Yeah, I accept that. I appreciate that. I'm not in that world, but this isn't about only top down. This is maybe a shift in balance, and maybe there are cases where there isn't enough of a certain technique.
Yeah, I was gonna agree with that. I have to admit, like when presenting on this pressure perturbation concept, also comes with a bit of guilt because I know I'm introducing like another thing to ice nucleation, which is already really complicated. But like in terms of the topic of this session, like can we even observe microphysics? Observing when the ice forms in mixed phase clouds is something that we can't really observe it directly, and there's still a lot of questions on how the initial ice particles can form. And so I think it depends also, yeah, like on the space, because I think for something like ice nucleation, is a lot of room for ground up work to understand how the ice is forming. It's just such a big elusive question, but maybe other parts of the climate system it's like more simplifying moment or